ಸರಿ. ಯಾರು? ಫಸ್ಟ್ ಇಯರ್ ಅಲ್ಲ, ಗುರು ಸರ್ ಅಲ್ಲ. ಎಂತ ಮಾರೆ ಆಗ್ಲಿಲ್ವಾ? Ganesh Pai? ಅದು ಅವ್ರದ್ದು ಸ್ಪೀಕರ್ ಇದು ಶೇರ್ ಮಾಡ್ತೀಯಾ? ನಾನು ಟೈಮ್ ಆಯ್ತು. ಪಾಸ್ವರ್ಡ್ ಹೊರತಿರ್ತೀನಿ. ಬಂಡಿಗೆ
ಹಲೋ ಸರ್, ಎಲ್ಲಿದ್ದೀರಿ ಸರ್? ಸರ್ ಇವತ್ತೊಂದು ನಿಮಗೆ ಮಾರ್ನಿಂಗ್ ಒಂದು ಸ್ವಲ್ಪ ಕೆಲಸ ಇದೆ. ಏನು ಗೊತ್ತಾ, ನೀವು ಬರುವಾಗ ಇವ್ರ ಹತ್ರ ಸರ್ಫ್ರಾಸ್ ಹತ್ರ ಹೋಗಿ ಬನ್ನಿ. ಅದನ್ನ ಅಡ್ಮಿಷನ್ ಇದ್ದೊಂದು ಸ್ವಲ್ಪ ಡ್ಯೂಟಿ ಸರ್. ಇವತ್ತು ಬೇರೆ ಯಾರು ಇಲ್ಲ, ನಿಮ್ಗೆ ಒಂದು ಬೆಳಿಗ್ಗೆ ಒಂದು ನಿಮ್ಗೆ ಡ್ಯೂಟಿ ಇದೆ. ಏನಿಲ್ಲ, ಅವ್ರು ಬರ್ತಾರಲ್ಲ, ಸ್ಟೂಡೆಂಟ್ ಬರ್ತಾರಲ್ಲ, ಆವಾಗ ಸರ್ಫ್ರಾಸ್ ಹತ್ರ ಒಂದ್ಸರಿ ಕರ್ಕೊಂಡು ಹೋಗಿ ಡಿಸ್ಕಸ್ ಮಾಡ್ಲಿಕ್ಕೆ ಅಷ್ಟೇ. ಅಡ್ಮಿನ್ ಕ್ಲಾಸ್ ಅಲ್ಲಿ ನೀವು ನಿಂತ್ರೆ ಆಯ್ತು, ಅಲ್ಲಿ ಕೂತ್ರೆ ಅಲ್ಲಿ ಇಟ್ಟಿದ್ದಾರೆ. ಜಸ್ಟ್ ಸ್ಟೂಡೆಂಟ್ಸ್ ಬಂದಾಗ ಅವರನ್ನು ಕರ್ಕೊಂಡು ಬಂದು ಇವ್ರ ಹತ್ರ ನಮ್ಮ ಸರ್ಫ್ರಾಸ್ ಹತ್ರ ಮಾತಾಡ್ಸೋದು ಅಷ್ಟೇ. ಅದೀಗ ಒಂದು 10ರಿಂದ ಸ್ಟಾರ್ಟ್ ಬರ್ತಾರೆ ಸರ್. ಒಂದೇ ಎರಡೇ ಹೀಗೆ ಬರೋದು.
ಹಲೋ ಹಲೋ. Hello. Good morning. Ganesh Pai, can you hear? Hello. ಎರಡು ಎಂತಕ್ಕೆ ಅಲ್ಲಿ ಒನ್. ನಿನ್ನೆ ಅದು ಯಾರು ಗೊತ್ತಾ? ಇಲ್ಲ ಇಲ್ಲ, ಯಾರು ನಂದು ಅವನಿಲ್ಲ. ನಾನು ನೋಟ್ ಮಾಡಿ.
ಕೇಳಿಸ್ತದ ನೋಡಿ ಮೇಡಮ್, ಕೇಳಿಸ್ತದ ನೋಡಿ. Official. Mic check. Mic check. Mic check. Mic check.
Good morning, all of you. I wholeheartedly welcome Dr. Guru DS, Professor Computer Science, University of Mysore, who will be the main speaker of today's morning session.
Good morning, sir.
Good morning, sir. Good morning, madam. Hello.
Right time ಗೆ join ಆಗಿದ್ದೀರಿ.
So we'll start the session in 7 minutes.
ನಾನು ಒಂದು 10:30 ಮೇಲೆ ಬರೋಣ ಅನ್ಕೊಂಡಿದ್ದೆ. ಏನೋ ನೀವು ಪಾಪ ನೆನ್ನೆ ರಿಮೈಂಡ್ ಮಾಡ್ಬಿಟ್ಟು
ವರಿ ಆಯ್ತು ಒಂದು ಸರಿ ಮತ್ತೆ ಗೊತ್ತಾಯ್ತು. ಸರಿ, ಒಂದು another 7 to 10 minutes ಅಲ್ಲಿ ಸ್ಟಾರ್ಟ್ ಮಾಡೋಣ.
ನೋ ಇಶ್ಯೂ.
ನಾನು ಮತ್ತೆ ಜಾಯಿನ್ ಆಗ್ತೀನಿ ಸರ್.
ಶೋರ್.
Guru sir. Hello sir.
Yes.
ವಾಯ್ಸ್ ಮತ್ತೆ ವಿಡಿಯೋ ಜಸ್ಟ್ ಚೆಕ್ ಮಾಡಲಿಕ್ಕೆ.
ಹೇಳಿ ಏನಾಗಬೇಕೀಗ?
ಅಲ್ಲ ಆಡಿಯೋ ಈಸ್ ಓಕೆ, ವಿಡಿಯೋ ಇಫ್ ಇಟ್ ಈಸ್ ವಿಸಿಬಲ್ ಬರ್ತಾ ಅಲ್ಲ? ಓಕೆ ಸರ್, ಥ್ಯಾಂಕ್ ಯು.
ಇದು ಸ್ಕ್ರೀನ್ ಶೇರ್ ಮಾಡ್ತೀನಿ ನೋಡಿ, ಬರ್ತದಾ?
ಓಕೆ ಸರ್.
ಬರ್ತಿದೆಯಾ?
ಇಲ್ಲ ಸರ್, ಬಂದಿಲ್ಲ.
ಒಂದು ನಿಮಿಷ. ಈಗ
ಬಂತು ಸರ್.
ಬಂತಾ?
ಹೌದು
ಬಂದಿದೆಯಲ್ಲ?
ಸರ್.
ಹಲೋ,
ಬರ್ತಾವೆ ಸರ್.
ನಿಮ್ದೇ ವಾಯ್ಸ್ ಬ್ರೇಕ್ ಆಗ್ತಿದೆ ನನಗೆ.
ಹಲೋ, ಕೇಳ್ತದೆ ಸರ್?
ನಿಮ್ದೇ ವಾಯ್ಸ್ ಬ್ರೇಕ್ ಆಗ್ತಿದೆ ನನಗೆ.
ಹಲೋ, ಕೇಳ್ತದೆ
ಹಾ,
ಸರ್?
ರೈಟ್, ಹೇಳ್ತಿದೆ.
ಓಕೆ, ನಿಮ್ಮ ಸ್ಕ್ರೀನ್ ಕಾಣ್ತಾ ಇದೆ ಸರ್?
ಕಾಣ್ತಿದ್ಯಾ? ಓಕೆ.
ಹೌದು.
ಇದೇ ಇರ್ಲಾ, ಸ್ಟಾಪ್ ಶೇರಿಂಗ್ ಮಾಡ್ಲಾ?
ಓಕೆ ಸರ್.
ಹಾ,
ಓಕೆ ಸರ್.
ಏನ್ ಮಾಡ್ಲಿ?
ಸ್ಟಾಪ್ ಶೇರಿಂಗ್ ಮಾಡಿ ಸರ್.
ಬಂತಾ?
ಹೌದು ಸರ್.
ಹಿಂದಲ್ಲಿ ಸೌಂಡ್ ಆಗ್ತದೆ.
Mic check. Mic check. Mic check. Mic check. Mic check. Mic check. Mic check.
Audio check. Hello.
Check.
Guru sir. Hello.
Hello.
Sir, shall we start, sir?
Why not? You just look at the participants and see. How many are actually enrolled?
62 ಬರ್ತಾರೆ ಸರ್. ಈಗ 27 joined already.
27, I think not all of them are from your side participants ಅಂತ ಕಾಣ್ತದೆ.
ನೋಡೋಣ ಒಂದು 5 minutes wait ಮಾಡೋಣ ಸರ್.
ನೀವು ಹೇಗೆ ನೀವು ಜನರಲಿ ಏನ್ ಮಾಡಿದಿರಿ ನೆನ್ನೆ ಮೊನ್ನೆ ಎಲ್ಲ ಆ ಕಲ್ಚರ್
we will start sir, they join ಅದಕ್ಕೆ.
Okay, fine.
Mic check.
ಇನ್ಮೇಲೆ ಇಂತ FDP ಮಾಡ್ಬೇಕಾದ್ರೆ
ಎಸ್ ಸರ್,
ಆನ್ಲೈನ್ ಬ್ಲಾಕ್ ಆಗತ್ತೆ 9:30 ಅಂತ ಹೇಳ್ಬಿಡ್ಬೇಕು ನೀವು.
yes sir, we will take your suggestion. We will take your suggestion. That's good suggestion.
ಅಲ್ಲ ಮಾಡ್ಲೇಬೇಕದು. ಎವ್ರಿವನ್ ಶುಡ್ ಕಮ್ ಅಟ್ ಲೀಸ್ಟ್ 10 minutes early ಅಂತ ಹೇಳ್ಬೇಕು. ಇಲ್ಲಾಂದ್ರೆ ಫ್ಯಾಕಲ್ಟಿ ಸರ್ಟಿಫಿಕೇಟ್ ಹಾಕೊಡ್ಬೇಕು. ನಾನೆಲ್ಲ ಆರ್ಗನೈಸ್ ಮಾಡೋದು ಹಂಗೆ ಮಾಡೋದು. ಟೈಮ್ ಮೇಂಟೆನೆನ್ಸ್ ಇಸ್ ನಾಟ್ an attitude of a teacher and unfit to be a teacher ಅಂತ ನಾನು ಹೇಳೋದು. ಅಲ್ವೇನ್ರಿ ನಾಗೇಂದ್ರ ಸ್ವಾಮಿ?
Yes sir. ನಾಗೇಂದ್ರ ಸ್ವಾಮಿ.
ಆಮೇಲೆ ತಿಂಡಿ ತಿಂದ್ರಾ
ಸರ್?
ತಿಂಡಿ ತಿಂದಿದ್ದೀರಾ ಹಂಗೆ ಕೂತ್ಬಿಟ್ಟಿದ್ದೀರಾ ಅಂತ? ತೊಂದ್ರೆ ಇಲ್ಲ. ನಿನ್ನೆ ಮೊನ್ನೆ ಎಲ್ಲ ಏನ್ ನೀವು 5 ನಿಮಿಷ ಲೇಟ್ ಆಗಿ ಮಾಡಿದ್ರೆ ಲೇಟ್ ಆಗಿ ಸ್ಟಾರ್ಟ್ ಮಾಡೋಣ, ತೊಂದ್ರೆ ಇಲ್ಲ. ಐ ಆಮ್ ರೆಡಿ ಫಾರ್ ಇಟ್.
A very good morning to one and all. I, Professor Ganesh Pai, Department of Computer Science and Engineering, welcome you all to the 4th day of online short-term training program on machine learning for societal applications. Before we begin with today's session, I would like to kindly remind all participants to mute your audio and video for a smooth flow of the program. If the participants are having any queries, you can drop your questions in the chat box. It will be conveyed to the speaker at the end of the session by our coordinators. If there are several queries, the answers will be mailed to all the participants. Attendance link will be shared in every session in Zoom and YouTube chat window, and participants are requested to submit your attendance. First half of the morning session will be engaged by Dr. D.S. Guru on feature selection approaches from 9:30 to 11 a.m. Followed by will be a break. Post-break session will be engaged by another eminent speaker, Dr. T. Nagbhushan, SJCE, Mysore, on neural networks. Dr. T. Nagbhushan will be continuing the session post-lunch too. With a short summary of today's schedule, we shall now commence our morning session. We are honored and privileged to have a most eminent and distinguished speaker in the morning session of 4th day, Dr. D.S. Guru, Professor at Department of Studies in Computer Science, University of Mysore. Now I request Dr. Sharmila Kumari to introduce the speaker, Dr. D.S. Guru, to our participants. Over to you, ma'am.
Respected sir, firstly, I would like to mention that it is an honor for us for having accepted our invitation to deliver a talk on teacher selection approaches in our training program. Dear participants, wishing you a very pleasant morning. At the outset, I would like to mention that we have with us one of the eminent academician and a researcher, Professor D.S. Guru, known as Guru in the research community. Dr. D.S. Guru is a professor in the Department of Computer Science, University of Mysore, and currently on sabbatical leave and associated with Naimo Technologies Private Limited, Bangalore, as a senior research scientist. He is formerly worked as a chairman, Admission Reformation Committee, chairman, Department of Studies in Computer Science, director of Distance Education, director, Internal Quality Assurance Cell, chairman, Board of Studies in Computer Science at University of Mysore, Manasa Gangotri, Mysore. Professor Guru has obtained his PhD from University of Mysore and carried out his postdoctoral work at Pattern Recognition and Image Processing Lab, Michigan State University, USA. He is a fellow of Boys Cast, Department of Science and Technology, Government of India for the year 2005, Award for Young Scientists from Government of India. Recipient of first ARP Award under Engineering Sciences, Vision Group of Science and Technology, Department of Science and Technology, Government of Karnataka, India for the year 2010. Recognized as Best Ethical Teacher at Higher Education by Rotary, Mysore for the year 2011. Best Student Paper Presentation Prize in 1992 during Master's Study, Computer Society of India, Bangalore chapter. Professor Guru successfully guided 19 students for their PhD degree and currently supervising 6 PhD students. He published 80 plus research papers in reputed journals and 280 plus conference papers, and right now having H index 25 with 2,436 number of citations. He is a member of advisory boards, program committees of ICDR 2017, ICDL 2018, ICCR 2005, 2008, 2011, 2016, ICMCCA 2011, and many more AI-related conferences. He is the associated editor for the Journal of Pattern Recognition, Elsewhere Science, and have been a reviewer for many journals, IEEE Transactions, Elsewhere, and Springer. Professor Guru edited several books, including Medical Imaging, Artificial Intelligence, Image Recognition, and Machine Learning Techniques, CRC Press, Taylor and Francis Group, 2019. Data Analytics and Learning, Springer, Netherlands, LNS, 2019. Cognition and Recognition, Springer, Singapore Publishers, India, 2018. Multimedia Processing, Communication and Computing Applications, Springer, India Publishers. Signal and Image Processing, Proceedings of ICSIP, Excel India Publishers, India, 2009, and authored Problem Solving with C, PHI Publications, 2018. Object-Oriented Programming with Java, PHI Publications, 2017. Object-Oriented Programming with C++, PHI Publications, August 2014. Professor Guru edited journals, namely International Journal of Machine Intelligence, Volume 3, Issues 3 and 4. He is professionally recognized very well and nominated by MHRD, Government of India, as a member of Board of Management, Institute of Medical Sciences, deemed to be University, Maharashtra, and invited to deliver keynote talks, seminars, and speech at many international conferences, seminars, and workshops, including human resource development centers in India and abroad. His entrepreneurship are many, which include founder trustee of Maharaja Education Trust, registered Mysore, established various institutions in and around Mysore, including engineering colleges, Maharaja Institute of Technology, Mysore, and Maharaja Institute of Technology, Tandavapura, and providing social service in villages. He is the founder president of Seva Samiti in their village, organizing several personality development programs for school children and medical checkup camps for villagers and actively involved in cultural development programs. I wholeheartedly welcome Professor Guru and request Sir to enlighten us with his authoritative lecture. Sir, with this introduction, I welcome you, sir.
Thank you, Madam Sharmila. Thanks to Ganesh, sir. Shall I share the screen now? Am I audible?
Yes, sir.
So,
Visible, sir.
is it visible?
Yes, sir.
Okay. Good morning to one and all.
Good morning, sir.
So it's I feel I'm respected, honored for having extended invitation to me to share my little experience which I could gain because of my personal research and also because of the research work carried out by more than a dozen of my research scholars for the last 2 decades with you people. The topic of my discussion today is on feature selection approaches. Of course, don't expect me to take into the more mathematical details associated with these feature selection approaches, but however, to touch upon the basics of feature selection, why, how, what are all the different classes of feature selection approaches available in literature, and in what way you being a researcher can think of extending these basic fundamental approaches to suit your specific domain and application in A&I below. So it's like going for a small walk inside a garden, getting familiar with various kinds of flowers, time being available in the garden, because tomorrow the plantation of new flower species may change a look of the garden in a different style, but still, what is the basic skeleton of the garden? What is the overall plans in the garden? So the garden that I'm talking about is what is called feature selection approaches. Probably for the last 3 days, having attended this FTP, you must have understood the things, especially on various stages of machine learning. And indeed, yesterday, Dr. Shekhar had made my job of introducing you the strong background of feature selection approaches simple by highlighting the advantages of dimensionality reduction techniques while talking about principal component analysis. So as these coordinators introduced me to you, I am from basically University of Mysore, but currently working for my research activities towards industrialization, towards productization of my research thoughts in association with one of the computer vision industries called Nanotechnology Bangalore. So probably in my lecture, I may also quote a couple of examples or the applications that we have been exploring in the industries, and also highlight what are the interesting, challenging issues that you can take up as your research topic to further explore. So before I begin explaining you the approaches of feature selection, let me just recollect the things which perhaps you must have discussed in the last 3 days. Any pattern recognition or machine learning approach involves basically 2 steps, majorly 2 phases. One is training phase, the other one is recognition, you can call it as, labeling, you can call it as, relabeling, you can call it as, classification, you can call it as, right? So we have what is called a reapplication of what we do.
Hello, sir. You are not audible, sir. Hello. Hello.
Hello.
Sir.
I think something went wrong, is it?
Yes, the connection.
Yeah.
Yeah. Is it fine now?
Yes, sir, visible, sir.
So in the training process, the interest lies in giving a computing technology a rich knowledge base on the population of my interest, on the samples of my interest. So during this training phase, what do? We just get a couple of samples of our interest. Probably the samples could be the samples related to face recognition. Then we collect sufficient number of samples of face images of variety of people, different people of our interest in different poses, in under different lighting conditions, right, and so on. So when we collect such samples, then we just give them for some pre-processing. During pre-processing, we just try to eliminate some noise present in them, some unwanted things, and or indirectly what Dr. Nagendra Swami said yesterday, that data cleaning or data preparation. We do a kind of data preparation during pre-processing, and then we subject it for a kind of feature extraction. Feature extraction is a method of transforming or that unstructured data into a structured representation. So during feature extraction, you can think of different types of features depending on the application in hand, but generally we advise you to extract all possible kinds of features, right? Like, while introducing myself to you people, these two coordinators went on telling about myself, right? My bio, my background of education, where I have come from, what I am today, where I am working for, what are my social, responsibilities, etc. But all features that they have spoken out about myself may not be of relevant features to you people, because it is an academic sector. You don't mind whether I am providing really a good service to the society or not, but you look at what are my credentials as well as my research contributions are concerned, right? So probably that's what is called. So initially we just go for describing. I mean, extract all possible varieties of features from each sample of your interest, and then think of selectively choosing something of your interest. Selectively choosing some features which really appear to be rich in accomplishing your task, right? That's what is called dimensionality reduction. Yesterday, Professor Nagendra Swami was narrating a story of classification, telling us that, assume that there are n number of features. I mean, I have a vector of n dimension. So there are n characteristics, n attributes you would, n attributes, n characteristics. The fundamental question is that n really required? If that n is too large, should I have to go to work with such a large number of features, thousands of features? Can I reduce it? Then perhaps in the afternoon session, Dr. Shekhar highlighted that you can think of transforming that features n dimension to some other lower dimension, so that you will have less number of features but still representing the same data of my interest, right, without any loss of generality. That's what is called dimensional reduction, which is the topic of today's discussion, especially a specific kind of dimensional reduction technique called a feature selection. Once those features have been selected, or less number of features have been derived out of it, then we just inject into a learning model, and in parallel there are domain experts which are helping us in labeling these unknown samples for the purpose of training. And with the support of those domain experts, and these learning models will be created, and they will be reposited in the form of an index if this corpus happens to be so large. So we go for indexing to speed up the activities, and along with the images and the labels generated from the domain experts, we accommodate with a kind of annotations in the large corpus. That's what is called the outcome or a output of a training phase. I mean, this corpus, what you look at on the right side of the slide, is the knowledge base out of my learning. Once learning is done, we go with a relearning. Similar samples will be given, but domain experts do not get involved in this process of relabeling or recognition or retrieval. So we generally call it as a classification phase, and we pass through the same pre-processing. We prepare the data again with the similar approaches and extract the same features and subject it for dimension reduction. I mean, these are all the models which were learned and selected during training phase, and the same models are now executed, and we come out with a reduced feature vector. And this reduced feature vector will be given as an input to the classifier. Classifier could be a Bayesian classifier could be nearest neighbor classifier. That's what we discussed yesterday, right? And that classifier works with the corpus. The corpus gives the knowledge to that classifier. The classifier job is to match this unknown vector, a reduced feature vector, which is given as input to it against already stored, right? Okay, the way in which it behaves, the style with which it behaves, the speed with which it behaves, the way in which it learns and attains the job, that decides what type of classifier it is. Is it a lazy classifier, or an active classifier, or a neighborhood based classifier, or a probability based, or a neural network? That's a different question. But now, given is a reduced feature vector, that reduced feature vector has got to be matched against what the vectors which were already learned yesterday during a training phase. And based on that matching, we just retrieve the top k based on the degree of matching, and probably when it is a problem of recognition, the rank one is considered to be the one or declared to be the ultimate. Otherwise, you can list them based on the priority. Look, dear friends, today's interest is on how well I can think of attaining this dimensionality reduction. So what are the different approaches available for dimension reduction in general, right? And where does this feature selection really suit? Why that feature selection is so important today in spite of deep learning architectures, right? That's my fundamental question to be answered today. So dimension reduction in general, if I just say that any training phase create this two-dimensional matrix. Look, the rows in this matrix are nothing but the samples, I mean feature vectors. Column in this matrix are nothing but the features. Let there be n number of features extracted from m number of samples. Then we end up with m cross n matrix, right? This matrix is to use because m is very big, lakhs of samples I have, and n is also big, thousands, in terms of thousands, I have 1,000 number of features. Then the question is, can I think of compressing it either in horizontally or vertically, right? I can think of reducing the matrix size. Either you can make m smaller, selectively choosing the samples as a representative, or you can think of reducing the number of columns by selectively choosing the column or transforming all n columns to a different d columns where d is considerably less, right? Far less than the n value. So look at, if you compress this way, reducing that m to some c, where c is very far less than m, right? Independent of sample sequence, irrespective of the sample sequence, then I say it's a cluster approach, which you must have discussed in second day of your FDP. So that's what is called reducing this matrix, right? All in all, so that number of rows become less when compared to the original. On the other hand, yesterday Professor Shekhar has spoken about 2 hours, especially on PCA, which transform this n dimension to some lower dimension, right? Some lower dimension. So that's what is called reducing the number of columns. So that reduction in are accomplishing some level of reduction in the number of columns in the pattern matrix or in the feature matrix is what is called dimensionality reduction. So dimensional reduction is nothing but crashing of n features to d features, where d is considerably less, very, very less when compared to n, far less than n. So what are the advantages? I need not explain you because Shekhar has narrated in an interesting way, in a beautiful way, the advantage of DOR, right? I can just simply pass through it. So I can assure reduction in memory. The data analysis becomes simplified because I like to work with less number of features. A cluster analysis or classification, classifier design becomes much easier instead of working with, clustering of samples which are, described with n number of features, right? So you are working with only d number of features, very less when compared to that. Obviously, your cluster analysis works faster, right? Similarly, classifier design becomes simple. So if you can reduce it to 2 dimension, only 2 features, then visualization becomes really possible, right? So instead of visualizing your sample space, in feature space of dimension 10, if you can visualize the samples in a feature space of plane, a 2D, then perhaps visualization can be more effective. So all in all, we can think of time efficient classifier. These are all the advantages of dimension reduction. But look at one end, we are telling that as the number of feature increases, the accuracy in classification the effectiveness in accomplishing the task also increases. But unfortunately, as you continue increasing the number of features, because the newly added feature may confuse the classifier, right? Because the newly added features may be the features which describes not only the samples of class 1, but also the samples of class 2, right? Almost equally. In such cases, that addition of a new feature perhaps puts the classifier into confusion, though that classifier will have some failure in classifying samples of different classes. In such cases, it is better not to add up some new features. I mean, of course, the accuracy of classification improves as the number of features increases, and after some time it starts deteriorating. At what time it deteriorates, that decides. I mean, you have to understand here, one is the difficulty in handling. The difficulty in handling any situation increases as the number of features increases. On the other hand, efficiency of a classifier also increases. Then you have to work in reverse and find out a crossover point, and that crossover point could be an interesting point to decide the number of features to be used. Anyway, what type of features, how many features to be is really confusing job. Nobody even today has any knowledge, so that there can be some analytical closed form, a mathematical way of expressing, finally automating the task of deciding how many features are really good. Only thing, you have to study the data that you have. You must have a strong knowledge on the application of your interest, and with the background of domain knowledge, perhaps you can be so good in deciding what should be the good number of features. Now, if I speak about dimension reduction methodologies, basically we have two categories. One is feature selection. Feature selection, name itself indicates selecting some of the available. I mean, selectively choosing few out of several. I mean, I have a set of 10 features. I'm not interested in all 10. I'm interested in only 4. Then which 4? I got to select. I mean, this feature selection results with a subset of the original. Hence, it is also called feature subsetting. On the other hand, I have 10 features. I don't want to selectively, choose some of them. Instead, I just work out a function which takes all these 10 as input and then converts this 10 into some other 5. Then I say a feature dimension is reduced, but after reduction, whatever the feature I will be working with, they are not original, they are the transformed. And such kind of dimension reduction techniques are called feature transformation. Yesterday you discussed principal component analysis, right? Principal component analysis transforms n-dimensional features into m-dimensional less number of features. So this is called feature reduction. So look at the complexity of feature selection, because I said is basically a feature subsetting. It is a process of choosing D out of n features. Then I'm looking for a subset of cardinality D selected out of n number of features. So how many possible subsets are there for that set with n features? 2 power n possible subsets, right? It's a power set of it. So even for a reasonably sized n, if n equals 10, I am talking about only 10 features, then the possible number of subsets is 2024, right? Sorry, 1024. Even for a reasonably sized n value, n equals 10, the number of possible subsets rise up to 1000. Look at the complexity of that algorithm of generating all possible subsets and then verifying whether my classifier really performs wonder, for which subset it really performs better. I got to check with all possible subsets. I mean, I got to verify the performance of a system by running it 2 power n times. When n increases, this 2 power n exponentially grows, then it is practically not feasible, because it's an exponential time complexity problem. So practically it is indeed impossible to think of generating all possible subsets and then finding out the subset based on performance of the classifier while running it every time. Instead, we are looking for some approximation algorithm, some optimization algorithm, where I can selectively search for the subset of my interest. My interest may be a subset of cardinality 4. I don't mind if I end up with a subset of cardinality 5, but I expect both the subsets to be almost same as far as the performance of the system is concerned. That is what is called feature selection approach. So on the other hand, if I look at the feature transformation, here is a space called original features. Here is a space called original features, and you have to apply. For example, because you are familiar with PCA, a PCA could be the transformation. When you apply the PCA will transform into a new set of features. Basically, strictly speaking, and Dr. Shekhar also highlighted that issue, most of the times I don't canvas PCA as a dimension reduction, I just canvas PCA as a feature transformation technique. It just allows me to get myself replaced in a n-dimensional space. Instead of using this as a particular origin where I am standing and looking at all samples, but unfortunately from this point of view, when I look at all samples being here, probably I may not be able to see a couple of samples. Then I get myself adjusted, my position adjusted, so that I stand at some other position so that all samples become visible for me for classification. Then I got to recompute the coordinates of all those samples with respect to this new position. And the recomputed values are nothing but the transformed features. Then basically, strictly speaking, as far as principles of PCA is concerned, the PCA transforms n-dimensional vector to n-dimensional only. But while transforming, PCA would also advise us of all n-dimensional features, which are of really great importance and which can be given a least important, so that it gets us the features in a sorted way, so that you can end up selecting only the first few and neglecting the remaining. That's why the PCA can be also exploited for the beauty of feature reduction. So original features transformed to some other new set of features. I mean, these new set of features are not the subset of the original available, they are completely computed out of this. Every feature computed is supposed to be a function of every original, right? But whereas in the case of feature selection, hope I am making clear that in the case of feature selection, I have 1, 2, 3, I end up selecting 2 of this, or I end up selecting 2 of this. But in the case of transformation, all these 3 will be simply thrown out, but new set of features will be computed as functions of these 3. This is the basic difference, the fundamental difference between the feature selection approaches and feature transformation based feature reduction. Look, here is an example for you. I mean, I have a feature matrix where there are n number of samples and 10 number of features. So what does this feature selection do? It converts this matrix of size 6 cross 10 to a matrix of size 6 cross 9, 3. So here feature 2, the column number 2 is selected. Feature number 5, column number 5 from this is selected. Feature number 9, column number 9 is selected. Only these 3 have been selected, assuming that these 3 would perform better. Look, when it's a question of pattern recognition, or when it is a question of classification, classifying samples belonging to different classes as member of its own class, then my interest is not to go with the features which are so rich in describing every sample, but my interest is to go for selectively choosing only those samples which are rich in discrimination, right? Hope you are understanding that. I am looking for a particular sample which is so good, which is so rich in keeping a sample of class 1 away from the samples of class 2. Similarly, I am looking for another feature which is so rich in keeping the samples of class 2 away from all the samples of class 1. Then those 2 features are good enough for bifurcating, for separating the samples of class 1 from that of samples of class 2, right? So this is what is the philosophy behind feature selection. In feature selection, I am in search of those features which are so good in separating samples of different classes, right? So that's what is called a subsetting method. Look at here, X basically is a sample chosen from what is the space? Space is this, whereas in this new, the space is reduced to only 3, right? Only 3. So look in this particular table, I have taken a 8 number of samples. Let's assume that there are 8 samples where each sample has been described by 3 features. So look at, if I go with only F1, please try to understand, if I go with only F1, then the value of F1 being 1 confuses me between S1, S3, because both the sample S1 and S2 bear the same value 1 with respect to F1, and F1 cannot be used to uniquely identify these samples. Similarly, F2 also, because F2 confuses me between S1 and S2 because both the samples have got the same value with respect to F2. And F3 also same, 6 and 6, 16 and 16. Look, if I go for F3 based classification, then I cannot distinguish S3 from S4. I cannot distinguish S1 from S2 and so on. Instead of that, if I go with all the 3, look at 1, 15, 6. this 115.6 triplet doesn't repeat here. Hence, S1 is unique with respect to all the three. S2 is unique with respect to all the three. S3 is unique with respect to all the three. So then the question is, should I have to use all the three, or can I selectively choose, if not one, right, a pair of features, so that these 8 samples are still distinguishable? Then the feature selection would recommend that, look at, why do you go with F2? F2 is not at all required, just to differentiate these 8 samples. Then it says, go with F1 and F3. This pair, 1 and 6, will never repeat here. 1 and 16 will never repeat here, though 1 repeats, but the second feature helps us in distinguishing them, right? Where though F3 repeats 6 and 6, but the first feature would help us in distinguishing those two samples. Look at, instead of working with these 3, F1, F2, F3, I can think of working with only these 2. There is no loss of classification, right? If the classification algorithm gives you 90% accuracy while working with these 3 features, the classification algorithm would continue working with the same accuracy even after reducing the number of features to 2. But look at here, this 1, 6, I mean a pair, is a subset of this triplet, and 8, 6 is a subset of this triplet, and all these is a subset of this entire, this matrix is a submatrix of this, and hence this feature selection is called feature subsetting. I'm looking for the best subset to accomplish the classification without loss of its accuracy or generality in general. On the other hand, the feature transformation here. Look at these 3 features. If you use F1, then these 2 bear the same. These 2 bear the same. If you use F2, these 2 bear the same. These 2 bear the same. If you use F3, these 4 bear the same value, right? Okay, similar observation is true here also. Then if you use F1 and F2, then 1 and 5, 1 and 15, right? 1 and 15. Look, S5 also has 1 and 15. So then this pair is not possible. If 2 F3 pair, 15 and 6, 15 and 6, then this pair also will not help us. If you use F1 and F3, look at 1 and 6. Here is 1 and 6 again. I mean, neither F1 nor F2 nor F3. Neither the pair F1, F2, F2, F3 or F3, F1, right, would help in classifying these samples uniquely. I got to inevitably go for all 3 features. If I want 100% accuracy, if I want my classifier to work better, I got to inevitably go with all the 3 features. No subsetting would help me out. In such cases, I can think of recomputing some new values out of these 3, right? Then what do? I generate these 2 columns. New features, F1, small f1. This is completely a function of these 3. This 41 is computed out of 3 values, 1, 15, 6. How is this 41 computed? That's a different story. But this 41 is computed as a function of these 3 values. Similarly, 1458 F2 is also computed as a function of these 3 values. When these 3 values are given as input to this transformation T would end up giving me a pair of values, right? 41 and 1458. Similarly, when this triplet 8, 15, 6 is given as input to this transformation, then it ends up giving me 57 and 128. And similarly, all these triplets have been given as input to T got me a corresponding pair. And when you look at this pair, each pair is different from the other pair. Now, instead of working with these 3 features, what do? I just transform them into these 2 and continue working with these 2 features. Then I have accomplished a reduction in number of features from a triplet to a pair. I mean, basically, look at these 3 features are used as input to this transformation. The transformation function got me this F1 and F2. What is the transformation especially I applied here? Look at, this is the one with which you are all well familiar and studied in your high school, quadratic solver. What is this quadratic solver? I just thought of assuming that these are the coefficients of a quadratic equation. Then I say it is x square plus 15x plus 6 equal to 0. It is 8x square plus 15x plus 6 equal to 0. Ax square plus bx plus c equal to 0. These are not assumed to be ABCs. When these are assumed to be ABC, these F1 and F2 are taken to be the roots of that quadratic equation. So roots can be computed as x equals minus b plus or minus square root of b square minus 4ac by 2a. When ABC, a triplet, is given as input to that function ends up calculating 2 roots, and these are the 2 roots, of course scaled version of the roots multiplied by 100. Okay, look at this quadratic solver can be used to convert a triplet into a pair, but these roots are the functions of these 3 values. So this quadratic solver works like a transformation function. Like, strictly speaking, this quadratic solver can be used, can be called as a dimension reduction technique, because it doesn't transform you from a 3D to 3D. It takes you from 3D to straight 2D. Whereas in case of PCA, please remember, don't get confused. In case of PCA, you are moving from n-dimensional space to n-dimension only. But because you have got some knowledge on the way in which it transforms you and gets you the features sorted in order, you can selectively choose few out of several, but it doesn't strictly move you from n dimension to a lower dimension. Look at in this space, again let me go back and tell you, in this transformation, your input space could be of n dimension, output space could be of m dimension, n and m. If n and m are same, you continue to be in the same space. Same space, I mean a space of same dimension, but you get yourself relocated as a new origin. And with respect to that new origin, the coordinating systems, the coordinating values of those samples are recomputed. If m happens to be strictly smaller than n, then this T can be straight away called as dimensionality reduction technique. If m happens to be, sometimes we do this, m happens to be larger than n, I mean n can be 10, m can be 20, I'm moving from a lower dimensional space to higher dimensional, right? Then I say it is not a feature reduction, it is not a feature transformation. Of course, feature transformation, but not for reduction. It is a feature enhancement. It is not dimensionality reduction, it is a dimensionality enhancement. Sometimes we recommend you to go for enhancing the dimension for the purpose of subsequently reducing the dimension, right? I will come to that little later. So please understand here, this quadratic solver straight away takes you from a 3D to 2D, and such a kind of transformation is strictly considered to be classified to be a dimensionality reduction technique. Okay, so if I go with the feature selection methods, basically we have a filter method and then a wrapper method, a combination of these two, one filter, one wrapper, combine them and see that both will work together for better performance of the system. Or you can think of, instead of combining filter with a wrapper, wrapper with a filter, you take 2 filters and combine them, or you take 2 wrapper methodologies, right, and combine them, and that's what is called ensembled method. So filter method is basically called as learning algorithm independent. I mean, I select the features without keeping in mind which classification technique will be employed for my task. Whether I work with nearest neighbor, or I work with decision tree based, or I work with SVM, it doesn't matter. I don't look at it at all. I just look at the features, I do feature engineering, I end up selectively choosing couple of them, independent of learning algorithm, right? And that is what is called a filter method. So here, while selecting the features, I got to evaluate each feature. For the purpose of evaluating each feature, I got to think of some criterion, right? And I mean, take a feature by feature one at a time, subject that feature for evaluation, compute some score, and based on the scores that you obtain for all features, decide which features are really good for you. Right? It's exactly like selecting students for master's education. The students have completed their bachelor's degree and they apply for master's education. I have only 20 seats, but number of applicants are 100. Number of applicants, there are 100 applicants, who is interested, who are interested in taking up admission for master's degree. Then how do I selectively choose only 20? Then I rank them, I take the average score in their qualifying examination, or if necessary, I conduct the entrance examination. I take up the entrance score, I just normalize and then produce a rank list. Then I go with the top 20. I mean, somehow I should find a method of sorting of features based on their degree of discrimination, based on their ability to discriminate samples. And such as feature, selection criterion has got to be worked out. And based on that selection criterion, I got to rank the features. Once features have been ranked, then I go for selecting the top K of my interest, top 10 of my interest. And such a method which works independent of learning algorithm is what is called filter method. On the other hand, why I'm selecting? If I know in advance, I'm selecting for nearest neighbor classifier. I'm selecting features for SVM classifier because SVM has a different behavior when compared to nearest neighbor, and Bayesian classifier has got a different behavior when compared to SVM. The features which got selected for SVM may not be the good features for a Bayesian classifier. The features which got selected for Bayesian classifier may not be the good features for some other classifier. Then, if I got some knowledge on well in advance, what classification techniques I would be employing? If I stick on to that, why can't I think of making use of that knowledge as an added knowledge for ranking of features and then selectively choosing them? And such a feature is what is called wrapper. It wraps around a learning algorithm. Wrapper technique is purely dependent on learning algorithm. And performance criterion is required here. It's not a feature selection criterion. Here I got to work with the performance criterion of a classifier. Maybe accuracy, maybe F feature, maybe precision of that, maybe recall of it, or F measure of it, or it could be R norm of it. Any validity measure you have to decide, associate with the classifier, and every time when you select the subset, run the classifier and check with the performance of the classifier and choose the subset of the features which leads, which drives the classification model to perform maximum. And that technique is what is called wrapper technique. For example, see, in a national institute like IITs, national institutes, still our universities and colleges have not reached to that level. In national institutes like IIT, IIIT perhaps, there could be two teachers who are ready to offer a course on, let's say, data structures. I mean, the teacher T1, teacher T2, both are ready to offer course on data structure. Any students can enroll for any of these teachers, but the number of students who can, the number of students to be selected for each teacher is only 10. But interestingly, when you look at the background of teacher 1, he appears to be a teacher who loves data structure course, but unfortunately not with a strong background of mathematics. I mean, he teaches well data structure, but unfortunately, he doesn't represent data structure from the background of mathematics at all. He never thinks that set theory is useful, but he just narrates the story of data structure as if he is narrating a story. Whereas on the other hand, teacher 2 always, whenever he goes on dealing with any data structural aspect, he always brings in mathematics. He enjoys bringing in mathematics. Then the question is to select 10 for the teacher 1, 10 students for the teacher 2. While selecting a student for teacher 1, I prefer those students who are not that necessarily good at mathematics. Or I prefer the students who don't necessarily like mathematics. But whereas in the case of teacher 2, I have got to select only those students who love mathematics, right? Otherwise, they really find it very difficult to attend through his lecture. Look at, if there is a teacher, and with respect to the teacher, if I drive my method of selecting students depending on the teacher, then I say it is a wrapper technique, right? On the other hand, I don't look at the abilities of teacher. I just 10 students have got to be selected. How many students have applied? You just rank them, choose the top 10, assign with the teacher. That's what is called a filter. Then you must have understood that the method of selecting feature subset, keeping in mind knowledge of the classification algorithm, perhaps works better, Yes, obviously, in the literature, wrapper techniques have been demonstrated to be performing better than a filtering method for selecting, but unfortunately, while selecting a subset of features, we have got to run classification algorithm every time, and it leads to a time complexity. I mean, for a large collection, when we talk about big data, when we think of scalability of the problem, then wrapper technique doesn't suit in practicality. The filter techniques, being independent of learning algorithm, would suit the reality. So nowadays, we the researchers concentrating more on filter method rather than wrapper method, right? So this is the fundamental difference between filter technique and a wrapping technique. Another example could be, look at, there is an international cricket game. There is an international cricket match which is planned to be held in the month of December of this year. Then the Indian cricket team has got to be selected. While selecting 11 players of cricket, what do? I just choose 11 players who are the top performers of India. Right? Amongst all Indian cricketers, I just choose the top 11 performers and make a team. Whether it's a good team or a bad team, I just make a team. This is one way of selection. On the other hand, I just look at in the month of December, how many other countries are really participating. Then I come to know that there are other only two countries. One is from Pakistan, another one is from Sri Lanka. I mean, only 3 teams are involved. The other 2 teams are from Pakistan and Sri Lanka. I know the players of Sri Lanka and Pakistan, right? If I can choose 11 players of India who are great performer against, Pakistan and Sri Lanka, that turns out to be a better team, right? Look at selecting team members, keeping aside the opponent teams, or selecting team members, considering the opponent team, right? Both are entirely different. The end result should be different. But selecting team members, keeping in mind the performance of the opponent player, perhaps works better in building up a team. Similarly here, in feature selection, wrapper techniques works wonderfully well when compared to any filter method. But unfortunately, nowadays, because most of the applications involve large collection, right? Large corpus, wrapper technique is time inefficient. That doesn't suit the practicality. That's why we are talking about hybrid model. What do? Instead of going with a large dimension and running the classification algorithm many times for wrapping method, why can't I think of applying filter first, reduce the dimension from lakhs to 100, and then apply the wrapper so that wrapper becomes practically possible, right? So this is a fundamental differences between what is called filter and a wrapper. Hope I made it very clear. So if I now get into the filter design, basically it has 2 steps. As I already narrated, one is to rank the features. I mean, if there are n number of features, every feature has got to be subjected for evaluation. Once feature is subjected for evaluation, I end up computing a score. And I do it for all n. And based on that score, I just sort the features according to the relevance. I mean, the first fundamental step is end up selecting relevant features, right? How many are top after sorting? After sorting, you select 10 features, for example. But when you select the 10 features, the first 2 features, though are the top features, but maybe redundant features, who knows? They are one and the same. Because they are one and the same, they are ranked to be the first and second. So then you have to eliminate such redundant features after selection, right? So that's why a filter is basically 2-step process. One is a selection of relevant features, and the other one is subsequently eliminating redundant features. For example, I select 11 players for Indian team. Looking at their top performance, looking at their, what do you call it as international rankings. Based on the international ranking, if I just end up selecting 11 players, probably my Indian team may have only batsmen top 11. I mean, the Indian team will have all 11 players who are batsmen. That's not a good team, right? When you select one batsman, perhaps selecting the next batsman appears to be redundant, Then I want another person who is a good bowler to be added into the team, right? Then I think of eliminating 5 batsmen who appear to be redundant when compared to the other batsmen and bringing in the bowlers, though the bowlers are internationally at low rank when compared to this batsman. This is what is called the necessity of eliminating redundant features. Look, basically, a filter design involves 2 steps. One is selecting relevant features, and then amongst selected relevant features, reducing or eliminating redundant features. For example, for the purpose of selecting relevant features, I have to go for some dispersion measure. Here are the n number of features. Look at the slide. Here are the n number of features. Then what do? For this feature 1, I compute some score. Compute the score. The score can be how much is the variation this F1 preserves across all samples of the population, right? How much is the variation that F2 preserves across all samples of the population? Yesterday, Dr. Shekhar was talking about if the variance is Mean variance is 0, right? That's one concept. Another one is if there is no variation at all, if zero variance. If there is a zero variance, then all values across the samples are one and the same. In such cases, this feature has no relevance. Then assign with a score very negligible, very small. I mean, the first step is compute the score. For the purpose of computing the score, you have got to think of a criterion called feature selection criterion. It could be many. That's what I call it as a dispersion measure. Any dispersion measure for that matter. So use that and compute the score. Once scores have been computed, let's assume that V1 is a score computed for F1, V2 is a score computed for F2, etc. Vn is a score computed for Fn. Once these scores have been computed, then what do? I sort these features, sort the features F1, F2, etc. Fn based on these scores. Whatever which has got, suppose F4 is the highest among all these, then bring in F4 first. If V2 is the lowest, I mean the smallest among all n scores, then keep this F2 at the end. Just sort the features, right? Like Fi comes first, Fj comes next, Fk comes next, Fp comes next, etc. Fl goes at the last. So once these features have been sorted, how many features you want? Let's assume that m features I am interested in, where m is smaller than n, and choose those m features from the beginning, right? Choose those m features from the beginning. Look at, in case of feature transformation like PCA, for example, these n features will be converted into another n features. But while giving these features, listing out these features based on the eigenvalue, PCA would get you them sorted. Then choose the top m, right? To choose the top m. Now, among these m, some of them may be redundant, right? So how do I compute this scores? Use some dispersion. The dispersion measure could be mean absolute difference. What is this mean absolute difference? Look at this feature F1 has got n, has got values across samples. Let there be m number of samples. Then there are m values, right? Take the mean of that, right? Mean of that, and subtract every feature value from the mean. Every feature value from the mean, take the absolute value, compute the mean of that absolute difference. If that mean of the absolute difference is high, obviously there is a variation across samples of the population. Then you can use this mean absolute difference as one of the criterion to select the feature. So for whatever the feature where mean absolute difference is high, that could be listed first. Whatever the feature where the mean absolute difference of that feature is very small when compared to all other, that could be listed at the end in the sequence. And once sequence is produced, you just take top m, right? That's what is one criterion. The other criterion could be variance, right? You compute the variance of a feature, variance of the next feature, and whatever the feature which has got the highest variance will come first in the list, right? Then we have arithmetic geometric mean. I mean, take the arithmetic mean, add up all values of that feature across all samples of the population, that and then divide it by the number of samples. That is arithmetic. Multiply all values that feature has across all samples of the population, right? And take that root, nth root if there are n values. That's called geometric mean, right? And take this ratio of that. If the ratio is high, the feature is said to be highly discriminable. If the ratio is less, the feature is said to be of less discriminable, right? You can use this arithmetic and geometric mean also as one of the criterion. Or you can use mean median difference. Mean median difference means compute the mean of this feature and compute the median of this feature. If that mean median deviation is high, the feature is said to have high discrimination ability. If that mean median are one and the same, then that variation within the samples of the population is negligibly small. That doesn't suit your purpose of identifying uniquely the features which is capable of establishing high discrimination. So you can use mean median difference as criterion. You can use Fisher ratio. It's for supervised learning. I mean, look, these are all unsupervised learning. I don't use any knowledge on the class labels of the samples. Whereas in case of Fisher ratio, I use the labels of the class sample, right? So class labels will also be made use of Fisher ratio, right? So that's for supervised environment. Once these M features have been eliminated, have been selected, then you check whether F1 is correlated to Fj. If Fj is correlated to Fm, right? If Fi and Fj are one and the same, right? One and the same. When I look at the values of F5 across all samples, and when I look at the values of Fj across all samples, if not one and the same, look, if it is 10, it could be 100. If it is 20, it is 200. If it is 30, it is 300, right? Then it is just multiplied by 10. If Fj can be expressed as a function of Fi, then why do you want this Fj, right? Because that becomes a redundant. If one is expressible in terms of other, if one is dependent on the other, right? Then you can think of eliminating, and such features are called redundant features. Suppose I make a committee of 5 members, right? In a university or in a college, there is a committee to make some decision. I make a committee of 5 members, but there is one person called a leader, right? A captain of that. Then there are 4 members. Among these 4 members, look at, if the 5th one always says yes when the captain says yes. If 5th one always says no when the captain says no, I mean the 5th one goes with the decision of the captain, then do you think that the 5th one is really required as a member of the committee? No. And such a person is what is called a redundant person. In the committee, everybody has to have some discussion, before coming with some agreement. So that is individuality. As long as the features are individual and they are different from the others, we can retain. If you find something which is highly correlated with the other, remove one of them so that M can further be reduced to some D features where D is very, very small when compared to N. This elimination is done with the support of similarity measure. How similar the feature 1 with feature 2, how similar feature 2 and feature 3, how similar feature 3 and feature 1, right? If you find any 2 of them most similar, you eliminate one of them and keep the other one so that you can further reduce it. And this 2 steps is what is called a filter design. For the purpose of establishing a similarity, you can either go with the cosine similarity function or you can go for computing the correlation coefficient, any similarity measure for that matter. I mean, basically what you have got to understand is you can think of your own filter method for your own application. It's not necessary that you have got to make use of the standard, benchmark criterion which are available in the literature. Look at the data, look at the samples of your interest, understand the purpose of classification, and keeping that, you can think of your own filter, a new way of filtering of the features. Filters, as I said, is like a coffee filter. When you pour the coffee, the filter does what? It attenuates unwanted and allows only wanted. Similarly here, the filter takes all N features, allows only wanted features to pass through by blocking unwanted feature, right? Why can't you think of your own filter strategy? But when you attempt to design your own filter strategy as output of your research contribution, then you have to think. Basically, filter has 2 steps. One is selecting relevant feature. The selecting relevant features involves exploiting one of the feature evaluation criterion. That evaluation criterion could be your own new one, right? And subsequently eliminating redundant features. How do I check whether the feature is redundant with respect to others? You can think of your own criterion. If these 2 criterion happen to be new, then you can canvas that I have come up with the new filters, right? And which works better for my application, right? So that's what you can, you can think of coming out with your own filter design for application in hand. So you can also do, and this has been explored well. Instead of going with these 2 steps, you can follow in a different way. Anyway, I have n number of features, right? And on the second day, if I remember, somebody, some resource person, had given a lengthy explanation on data clustering. What do you mean by data clustering? Data clustering is nothing but identifying the internal relationship existing among the data. I mean, whatever the data which exhibit high degree of similarity are placed in one group. Whatever the data which possess less degree of similarity, I mean high degree of dissimilarity, will be kept in different clusters, right? Similarly, I have n number of features. Assume feature itself is a samples for me. Feature itself is a data for me. Then can I study how these features are related mutually? Then do a feature engineering. Instead of clustering the data sample, you cluster the features. When you cluster the features, you end up with some number of clusters. From each group of features, from each cluster of features, why can't you think of selectively choosing a representative, right? That could be a wonderful, filter concept today. So clustering of features, and then choosing cluster representative. For example, see here, I have a objects versus features. This is how conventionally in machine learning, we represent every pattern in terms of features, right? This is the data matrix. The data matrix has got to be transposed so that you will have each row a feature. Here, each column is a feature. Now, each row becomes a feature, and each column is an object now. Instead of clustering object, I go for clustering of features. When I do clustering of feature, either you can think of any agglomerative strategy or any partitional cluster. If you are, having some knowledge well in advance, how many features you are really interested in, right? I have 100 features, but I have got to work with only 7 features. If you are very particular about number of features to be selected, right, then you can go with any partitional k-means, fuzzy k-means, any partition clustering. But partition clustering requires an added knowledge on how many partitions you want. Either you can use agglomerative or you can use partitional. In that case, I want to generate D clusters. Then what does it do? It gets me the D clusters. Look, feature 3, feature 4, feature 21 are put together because they exhibit high degree of similarity. Whereas feature 31 and feature 14 are put together as members of the same cluster. Why? Because they possess high degree of similarity. But on the other hand, F3 and F31 have been placed differently because they exhibit high degree of dissimilarity or less degree of similarity, right? So the clusters have been obtained. Now, once clusters have been obtained, from each cluster, you choose a representative among these 4, which is the best one. Among these 3, which is the best one? Among these 2, which is the best one? There are many. Oh, which is the best? I mean, choose one among several, right? One cluster representative. The choosing cluster representative could itself be an interesting topic, right? Then what do you have to do? You have to establish a similarity and think of a graph representation and choose the center of the graph, right? That could be the best one. Choose the center of the graph. That could be the best one. Choose that. Right? So if you end up selecting only one, which is available here, like F1, from here F14, from here F21 I select. Then I end up selecting F4 from this group, F8 from this group, and F31 from this group, and some are from this group. Then I selected one thing. Another thing is, because these are all placed to be together as members of the same cluster, why can't I think of averaging of all the features, right? Look, I don't select F8, nor even F1, nor even F2. None of these get selected. Instead, something is computed out of these 4. A new feature. I take the average of all the features, right? Mean of all the features. And that newly computed one will be selected as representative. In that case, I don't say it is a feature selection. I say it is a feature transformation, right? It is a feature reduction, not through subsetting, but through transformation. For the purpose of transformation, I go for grouping of likelihood features, right? Similar features, and then average them, or I just compute something. That's what is called a transformation. If this selecting representative happens to be strictly one of these, then it is strictly feature subsetting, feature selection. Otherwise, it is called feature transformation. So you can think of this way of selecting features also. On the other hand, wrapper method. As I told you already, wrapper method is a method which wraps around the classification algorithm. You must have a knowledge and you have got to stick on to that. I am selecting these features to drive this classification algorithm. I mean, the selection is totally dependent on the subsequent learning algorithm, SVM. I end up selecting F1, F2, F3. If it is nearest neighbor, I may not end up selecting the same F1, F2, F3. It could be F5, F6, F7, right? Because every classifier has got its own behavior. And based on its performance, based on its behavior, I end up selecting different subsets. So here, wrapper methods are purely dependent on, right? Classification algorithm, learning algorithm. So basically, we have 2. One is sequential forward, the one which starts with a empty set and goes on constructing a subset of interest by adding up the features each stage. Whereas sequential backward selection, it starts with all the features and it goes for eliminating the feature. These are the 2 ways, right? I have 10 values. I got to end up selecting 3 values. One is selectively choose 3 and construct the subset of 3 values. Or among 10, you go on throwing out one by one, 7 times, you end up with the 3 values, right? That's what is called. One is a sequential forward, the other one is a sequential backward selection. Combination of this called ensemble. I mean, you can think of combining sequential forward with sequential backward, or you can think of combining sequential backward followed by sequential forward. So those are respectively called sequential floating forward selection, sequential floating backward selection. Those are generally called ensemble methods. If I just speak about sequential forward selection, look, it is a method of inclusion. It goes with the method of inclusion. I mean, it starts with an empty set. Initially, I have 5 features, right? Still, I am working with 5 features. Initially, the number of features selected is empty. Then what do? I have a classifier C. I decided SVM is my classifier. Then what do? I take only feature 1 first. Evaluate the performance of classifier SVM. What is the performance? 71%. F2, 68%. When I run the SVM with respect to F3, it is 55%. When I run the SVM with respect to only F4 feature, considering only F4 feature, then its accuracy is 43. When I run SVM with respect to F5, its accuracy is 49. But when I have executed SVM for classification by using feature F1, then it had 72%. Then which feature is working better when compared to other? F1. Then what do? From these 5 features, I end up selecting first F1. Now the features left out are these 4. Then what do? Which one can be added into this? Then I try F1, F2, evaluate the performance of the system. F3, F1, evaluate the performance of the system. F4, you add up F4, then take out F4, add up F5. Then you try with the pair, F1, F2, F1, F3, F1, F4, F4. Look at the complexity of wrapping technique now, right? Indirectly, if not all possible to pour in subset, at least some of them got generated, right? And each time when you evaluate it, I mean 4 times you executed here, and F4 appears to be a better feature to add up, then add up F4. Then go with the next. And each time, whether it ends up with improving. Earlier it was 72 when F1 alone is used. When F4 is added up, now the best performance is 78. Yes, improved. Go with that. When the another, again, you try adding F2, the triplet, adding F3, making another triplet, adding F5, making another triplet, and check the performance. The performance is now has become 88. Oh, now better. To add up the new one, that's called F5. Now the features selected are F1, F4, F5. Now I got to check with whether addition of F2 still improves or addition of F3 still improves or not. When I just checked with addition of F2 and also addition of F3, perhaps that 88 has come down to 63 when F2 is added up. When 88, when F3 is added up, 88 has come down to 82. Then however I try, it's not at all possible for me to improve the performance of the SVM classifier. Then it's better to stop with F1, F4, F5. So look, it starts with the empty set and goes with a method of inclusion. It always adds up a best feature such that the performance of a learning algorithm is maximized and stops when you cannot further continue. And that way of selection of features, constructing a subset, is what is called sequential forward selection. Notice here, you are not trying to generate all possible pairs. Here, you just have generated only 4 pairs where F1 is mandatorily used. But we never have checked, we never have come across with any circumstance where I have verified the performance of the system by considering F2 and F3, right? F2 and F3 pair must have been the most performing, wonderful pair. But unfortunately, because F1 got selected in the beginning, I mean, F1, when alone, considered, appear to be performing better. But F2, when alone is considered, appear to be performing less. But when F2 is used along with F3, perhaps the F2 works much better. But we did not have any such situation where we just have trained our model and verified the performance with a subset called F2 and F3. I mean, look, though it appears to be a model which generates possible subsets and verifying the performance of the system to select the best subset, but it doesn't generate all 2 power n subsets, only a subset of 2 power n subsets, right? Okay, so the which feature gets selected first, that matters a lot, right? Which feature gets selected first, that matters a lot in deciding the quality of the subset that you generated. That you have to keep in mind. So in case of backward selection, it works in reverse, a method of elimination. It starts with all features, all n features, right? And then go on eliminating the low performer, right? Low performer. I have got 20 members. but I got to end up selecting only 11. Then find out who is a low performer, worst among all. Then eliminate. Next verse, eliminate. Next verse, eliminate. Continue doing, right? So starts with empty, which is right. Nothing is eliminated. Then F3 is eliminated, and then F5 is eliminated, and so on. And then finally you end up with F2, F4. This works in reverse. Look, these two phenomena or strategies called selection, forward selection, sequential forward and sequential backward, though appear to be reverse in nature, they are not duals. Two processes P and Q are said to be dual if one works in the reverse of the other. Still, end results are same. But here, the sequential forward selection and sequential backward selection, though appear to be reversible each other, but strictly end results are not necessarily same for all applications. Hence, don't take them as dual strategies. So instead of going with only filter or only wrapper, you can think of hybridizing, right? As I said in my explanation earlier, you take the training data set, apply the filter method, reduce the dimension to a lower dimension, and then go with a wrapper, because wrapper suits better when the dimension of the space is reasonably less. Then apply the filter in case if you are working with very, very high dimensional space, apply the filter strategy, reduce the dimension to 100 and go with the wrapper, and then do the classification. So that's hybrid. Ensemble is take set of original features. Why you want to try with only one criterion for feature ranking? Use variance, use arithmetic geometric mean ratio, use what Fisher criteria in case of supervised, and think of generating the ranks 3 types, and then combine the ranks into single rank, and then reduce the data set, right? That's what is called exhaustive search. You can think of combining multiple criteria and together into single criterion, either with AND conjunction or with OR conjunction, and so on. I want to select a feature which is either ranked first or either ranked here or either ranked here as first ranking, right? Wherever it comes as first, that goes first. Or you take the rank number here for a particular feature, rank number here, it could be third one here, it could be second one here, it could be seventh one here, add up all the rank, divide by 3, that gives you the average rank. Based on the average rank, resequence the features and select the top EM, right? So that's method of combining, the same kind, filter to filter, wrapper to wrapper is what is called ensemble method. So sequential forward, look, it's a method of inclusion and elimination. I mean, ensemble method, sequential floating forward, whereas sequential floating backward. These are ensembled methods. Method of inclusion followed by elimination, whereas this one is a method of elimination followed by inclusion. It starts with empty set, whereas this starts with all features. So forward selection followed by backward elimination, whereas here backward elimination followed by forward selection. It is SFS plus SBS at each step, whereas it applies first SBS and then SFS at E. That's how, I mean, A comes first, then B, or use B first and then A. This is what is called method of ensembling wrapper technique. And basically we have only 2 types of wrapper technique. One is floating forward, another one is floating backward, right? So here is some, one example for you to understand how well the feature selection really help us. This is a old, results I'm putting perhaps 6-7 years back, what we have worked on medical images. This is a classification problem where there are about 5 classes, look, class 1 to class 5. And the features were color, texture, and RGB histogram we have taken up. Totally computed 4,182. I'm just showing you as an example, okay, extraction from our earlier work. So global features were computed, and number of samples for each class not necessarily balanced, imbalanced data class. So total number of samples used is 510. These are some example pictures of each class. Okay, how many features? Remember that it is 4,182. When the classification accuracy, precision, and recall and F measure were computed using all features, right, for a particular classification algorithm, these are the values, right? These are the values. When we have gone with feature selection method, MED, mean absolute difference, mean median difference, AMGM, arithmetic mean, geometric mean ratio, right? And this is the total variance. Look at the number which is put inside the bracket is the dimension selected. So instead of working with 4,182, the MAD technique has recommended only 3 features. Look at only 3 features, right? Only 3 features. Using those 3 features, this is the accuracy, this is the precision, this is recall, this is F measure. Similarly, using 3 features selected by MM method. This AM-GM has given us 8. That appears to be performing better than all. Look, with a dimension of 8, with a dimension of 3. So here are these. When compared to this, original result, here is this. Okay. So with 8 feature selection, 8 features. I mean, here what it quoted here is AM-GM. So when original results are compared with the results obtained by AM-GM, this is an improvement, right? Okay, as an improvement in each accuracy, precision, recall, F measure. So how many features we have used after selection? 8. Dimensional is reduced from 4,182 to 8. Look at the reductions, percentage. Like very high, 99% almost, right? So that's the advantage of going with the feature selection technique. Another example is this. Due to COVID-19, so we deployed a wonderfully well face recognition system for thousands of subjects, people working in some organization outside India as a part of industry, assignment. And the system was trained on, faces without masks. The system was deployed in the month of December 19 and January 2020. There was nothing like COVID-19 situation. The people have enrolled without any mask. So we have used deep learning architecture to select, to generate features. The number of features generated were 128 in number. Right? This is what example of a face image enrolled for recognition. The system was working wonderfully well, 100% result for thousands of people. But due to COVID, the people started coming with masks to the organization. No, the system, will stop working fine. Because the people are not ready to remove the mask. But when the face with mask is given, the people, the system used to fail in recognizing. Then the task is to make the system so capable of recognizing people looking at only this visible area of the face. Look at these 128 features have been extracted by considering entire face. Now, some features have got to be extracted only looking at this visible area. Then the question is, which are all the features out of 128 which are the representative of only this visible area? That's a subsetting problem, right? Okay. So let me not explain in detail. Then we did some subsetting way of doing it. Look at here are some examples: a face without mask and face with mask, right? So the person enrolled with this face but started coming with this, then still I expect the system to recognize, right? Okay, a person enrolled with this face, but earlier the system used to work even with a person enrolled without spectacle and without beard, but when person comes with spectacle and with beard, but now the person comes with a mask. How to make it? Then I get to selectively choose only those features which are representative of this area. But unfortunately, when the system is trained with the deep architecture, then subsetting is really a tough job. Then we just have tried it. Perhaps on Saturday I will present in a detailed way. So we just have gone with 128 features. Then the performance of the system when all 128 features are used is only 81%. Right? 19% were the failures. Earlier the system was working with 100%, but now 19% is the error. So mean difference, mean variance, these are the criterion used. 4 criterion, right? Look. Okay, number of features selected, not 128. Instead of 128, 90 features, 122 features, 75 features, 63 features, and so on. So then the accuracy, instead of 81.5, risen up to 90 point something, 84, 90, 89. Look at, there is always an increment irrespective of the criteria. Then what we have done, we just thought of going with a fusion, ensembled of features, filtering strategies, right? These 4 have been fused together to generate a re-ranking of the features. And when we are done with that, instead of going with 90 or 128 or 122 or 75, we just have thought of 74 top features, right? Which has given us an accuracy of 92.48. There is a considerable improvement, right? Earlier, the system used to work with 19% error. Now the system works with only 8% error, right? So feature selection. This is another example which recently we worked on, in a real-time application I'm talking about. Then the system deployed in a real-time application, and there were about 9 individuals who used to come to the office on alternate days, right? Because of COVID situation, all employees were not allowed to get into the office, only 9 at a time. So those, when we are verified the performance of the system, only for 9 people instead of considering all 1,000. Thank God that the system started working with 100% every day for the 9 subsets selected, right? So this is quite interesting, application we handled and made it possible in real-time application, our AI, right? So further, in our lab called DAL, Data Analytics and Learning Lab of Computer Science Department of University of Mysore, we have been pursuing, machine learning problems on various applications, and as a part of, a piece of the research work, and almost all applications we canvas towards feature selection. Look, dear friends, basically subsetting and transformation. Generally, when the data set happens to be large, transformations are not practically usable. Then feature selection. Under feature selection, we have subsetting and wrapper. When the dimension of the feature is too high, wrapper doesn't suit, only subsetting. When the subsetting is only filter. When the filter is used, then you can think of possibly many filters and fusing them together for effective way of selecting the subset of your interest. And then still you want to select the features relevant to a classification algorithm of your interest. If you are so particular about the classification algorithm, then I would recommend you to go with hybrid technique instead of an ensemble technique. Hybridize a wrapper subsequent to a filter. Apply the filter, reduce the dimension, and then go for wrapping technique by fixing up your classification algorithm. So we have been pursuing, these are all the list of publications. Recently, we just have come out with one publication in pattern recognition letters elsewhere journal, where we have recommended an alternative framework, especially for a supervised learning, feature subset selection for supervised learning, class dependent, then instead of generalizing the evaluation of a feature, why can't you study the feature with respect to a class? Then if there are k number of classes, for a particular class 1, try to find the best feature which is capable of keeping all samples of class 1 away from rest of the samples, right? Rest of the classes. Then select another feature, feature number 2, which is capable of discriminating not class 1, class 2 samples from all other samples. Then if there are k classes, you end up selecting only k features. So that is an alternative framework which we have selected for supervised learning. So this you can read. I'm sure it will motivate you to think in your own way of, or in your own method of selectively choosing the features. So we worked on even interval valued feature selection. You can see, and we got pattern action letters, another expert systems application elsewhere, yet another for online signature, writer dependent feature selection, and so on. I wish you just Google it in my name or in my laboratory name. I'm sure you'll get a list of papers published in reputed journals. Just read through. At least you will have some kind of inspiration, motivation, so that you also can think of, instead of adapting existing, you can also think of your own method of feature selection suiting your requirement. With this, if I sum up my lecture, hope I'm on right time. Yes. If I sum up my lecture, I started with notions of dimensional reduction, a general way of understanding it, and then discussed on filter methods, wrapper methods, specifically into feature selection, and hybridization of these two, ensembling of any one of these with multiple instances, and quoted 2 examples, basically one on medical image, skin image analysis, another one into face recognition applications. Friends, one thing you have to remember, sir, is it always possible to think of extracting or finding out such features which are so rich in discriminating samples? Is there any guarantee? Then I'm sure I would rather say, in my own philosophical way, look, there is always a distance. There is always a distance between 2 living things. Even in twins, there is a distance. There is some discrimination. At least mother identifies it, right? I may not be able to distinguish 2 twins, but mother does it. Look, there is always a distance between 2 living things, as it is unlikely that any 2 living beings are alike. No 2 can be alike. Otherwise, they are called single, right? As long as you say they are different, as long as you say they are 2, there must be something which distinguishes them. It is even true with artificially made objects, however they are visually alike. With this message, I'm sure you can boost up your confidence. Think of selectively choosing or searching for. But what is very important is, look, the mother searches for such a feature which is capable of distinguishing two kids which are twins, right? And that method of searching is supposed to be more effective and efficient. Look for that and go with that. With this, if I terminate, then perhaps my lecture appears to be incomplete. I get to extend my heartfelt acknowledgement specifically to the organizers, with a special thanks to Madam Sharmila for having given me an invitation to share my views on feature selection approaches, right? And I must also thank my research scholars, especially past and current, who have given me a rich experience to put the things in my own philosophical way. And more so important, my mentor, Professor Nagbhushan, who has boosted up confidence in me when I was doing my PhD work. With this, I thank you one and all. Thank you very much.
Thank you for such a wonderful session, sir. It was really superb session. The way the quadratic equation was linked to feature selection, I am sure it have had triggered the minds of participants to think in various diversities. With that simplified and the crystal clear explanation on various feature selection approaches, I no doubt admit you are rightly called guru in the research community, sir. Thank you once again, sir. Now we come to the question and answer session. So participants, I request if you have any questions, kindly raise your hands. After your hands are lowered, you can unmute and ask the questions. So first question to you, sir.
Yes, sure.
How feature selection is done when neural networks are used for classification technique?
Correct. So not only that, this is what I have used, deep learning architecture, So deep learning architecture gives some number of features. So feature extraction. That I will present on Saturday morning, right? So while exploring possible avenues for researchers to dig out in machine learning. So when neural network is used for classification purpose, assume that the neural network is working fine 89% or working fine 100% for n number of features. Then the input neurons are n in number, right? There are n values getting injected into the neural system. Then you can think of another neural network which work with less number of features, giving the same accuracy, right? Then obviously you have to go for selectively choosing the features. So even under neural network also, we do the feature selection. So that's what I presented here in first face recognition applications. Though the system was built completely on deep learning architecture, not only classification, even feature extraction was also through neural network. But in between, we just tapped the features and went on engineering, right? And then understood that instead of 128, it's good enough to use only 74. How did we do that? What are the alternative models? Perhaps I will touch upon that issue when I explore further avenues on Saturday lecture at 9:30, please.
Participants, any other questions? Kindly raise your hands. Okay, thank you, sir.
Fine.
Now I request Professor Ganesh Pai to take over.
Thank you, sir. It was an excellent session on feature selection approaches. I'm sure our participants have got several valuable inputs that will help them in their research work. You have clearly explained the various approaches of feature selection that is primarily required for any research work. We will be eagerly waiting for your next session, sir, on the 29th. Thank you very much, sir.
Sure.
So, dear participants, Dr. D.S. Guru sir will be joining us back on Saturday 29th with the topic research avenues in machine learning. I thank you again, sir, for today's session. It was
Thank you very much.
Thank you, sir.
Thank you. Shall I leave?
Okay, sir.
Thank you, sir.
Thank you, sir. So, participants, we shall now break for 30 minutes. We will resume our session at sharp 11:30 a.m. with the second part of the morning session that will be engaged by Dr. T.N. Nagbhushan on neural networks. Thank you.
Remind. Good morning, sir.
Good morning. Hello.
Hello, sir.
Is it audible?
Yes, sir.
There is some echo.
Yeah, there is sound.
Is this okay?
No, sir, still
Sir,
disturbances.
still it is.
Echoing, sir.
Is this okay? No,
There is echo effect, sir.
it's an echo effect. Okay. Is this okay?
Clear, sir.
Yes, sir.
Is it audible?
Yes, sir.
Yeah. Good morning to all of you.
Good morning, sir. Sir, shall we start, sir?
Yeah, another 5 minutes.
Okay, sir.
To wait for the participants to come.
Fine, fine.
Just mind this.
Yes, sir.
Should be okay now.
ನಮಸ್ತೆ ಸರ್ ಗುರು. ಸರ್ ನಮಸ್ತೆ, ಟೇನೇನ್ ಸರ್?
ಓ ನಮಸ್ತೆ ಸರ್. ನಾನು ನಿಮ್ದು ಲೆಕ್ಚರ್ ಕೇಳಿದೆ ಗುರು.
ಇವರ್ ಆನ್ಲೈನ್?
ಆನ್ಲೈನ್ ಒಂದ್ ಲಾಸ್ಟ್ ಅಲ್ಲಿ ಕೆಲವು ಬಂದೆ, ಫಸ್ಟ್ ಮಿಸ್ ಆಗೋಯ್ತು.
ಹೌದಾ?
ಸೊ ಬ್ಯಾಕ್ ಟು ರಿಸರ್ಚ್ ಇವಾಗ.
ದಟ್ಸ್ ಗುಡ್ ಥಿಂಗ್ ಯು ಹ್ಯಾವ್ ಡನ್ ಇಟ್ ಇನ್ ಲೈಫ್ ಅಂತ.
ಅಲ್ಲ, ಆಫ್ಟರ್ ಆಲ್ ರೌಂಡ್ ಎಲ್ಲ ಹೊಡಕ ಮುಂದೆ ಕೊನೆಗೆ ಬ್ಯಾಕ್ ಟು ದಿ ಫೇವರೇಟ್ ಏರಿಯಾ.
ಓಕೆ, ಗುಡ್. ದೇಶ ಎಲ್ಲ ಸುತ್ತಿ ನಮ್ಮೂರಿಗೆ ಬರ್ತೀವಲ್ಲ, ಹಂಗೆ ಸರ್ ಇದು.
ಅಲ್ಲ, ಅದೇ ಈ ಸಾಕು ಎಲ್ಲ ನೋಡಾಯ್ತಲ್ಲ, ದೇಶ, ಅಡ್ಮಿನಿಸ್ಟ್ರೇಷನ್ ಎಲ್ಲಾ ತರನು ನೋಡಾಯ್ತದ. ಆಲ್ರೌಂಡ್ 360 ಡಿಗ್ರಿ ಕಂಪ್ಲೀಟ್ ಆಯ್ತು ಇವಾಗ. ಸೊ ದ ಬೆಸ್ಟ್ ಟೈಮ್ ಟು ಎಂಜಾಯ್ ಇಸ್ ಡೂ ಸಮಥಿಂಗ್ ಅಂಡ್ ಹೆಲ್ಪ್ ಪೀಪಲ್ ಟು ಅಂಡರ್ಸ್ಟ್ಯಾಂಡ್ ವಾಟೆವರ್ ವಿ ನೋ.
ಕರೆಕ್ಟ್. ಅದೇನೋ ಒಂದು ಆಡಿದೆ, ಎಲ್ಲ ಸುತ್ತಿ ಬಂದ ಮೇಲೆ ನಮ್ಮೂರೇ ಚಂದ ಅಂತ, ಹಂಗೆ. ನಮ್ ತಗಡೂರು ಟೆಂಟ್ ಅಲ್ಲಿ ಕೂತ್ಕೊಂಡು ಈ ಹಾಡುಗಳು ಕೇಳ್ತಿದ್ವು, ಹಳೆ ಪಿಕ್ಚರ್ ಎಲ್ಲಾನು. ನಾವು ನಡ್ಕೊಂಡ್ ಬರ್ತಿದ್ವಪ್ಪ ಊರಿಗೆ.
5 ಪೈಸಾ ಕೊಟ್ಬಿಟ್ಟು ನೆಲದಲ್ಲಿ ಕೂತ್ಕೊಂಡು ನೋಡ್ತಿದ್ವಲ್ಲ, ಗೋಲ್ಡನ್ ಡೇಸ್.
ನಡ್ಕೊಂಡ್ ಬರೋದು ರಾಜ್ಕುಮಾರ್ ಮೂವಿ ಭಕ್ತ ಕುಂಬಾರ, ಅದ್ ಎಷ್ಟೊತ್ತು ಬಂದಿದ್ದೇವೆ ನಾವು.
ಎಕ್ಸಾಕ್ಟ್ಲಿ, ಕರೆಕ್ಟ್.
ಶರ್ಮಿಳಾ, ನಾನು ಸರ್ ಇಬ್ರು 4 ಕಿಲೋಮೀಟರ್ ಅಂತರದ ವಿಲೇಜ್ನವರು.
ಓ, ಅಷ್ಟೇನಾ ಸರ್?
ಪಕ್ಕ ಇದ್ದವ್ರು ನಾವೆಲ್ಲರೂ.
ಓನ್ಲಿ 4 ಕಿಲೋಮೀಟರ್ಸ್.
ಸರ್, ನಿಮ್ಮ ಊರ್ನವರೆಲ್ಲ ಇಂಟೆಲಿಜೆಂಟ್ ಅಂತ. ವೆರಿ, ನಮ್ಗೆ ಎಷ್ಟು ಖುಷಿ ಅನಿಸ್ತಿದೆ. ಇಷ್ಟು ಬಿಸಿ ಶೆಡ್ಯೂಲ್ ಅಲ್ಲ, ನಮ್ಗೊಂದು ಟೈಮ್ ಕೊಟ್ರಲ್ಲ ಸರ್, ದಟ್ಸ್ ಗ್ರೇಟ್.
Now that I am totally free, devoted to.
ಈಗ ಅದೇನೋ ಡೀನ್ಶಿಪ್ ಏನೋ ಇದೆ ಅಂತಲ್ಲ ನಿಮ್ಗೆ? ಈಗಲದೇನೋ ಡೀನ್ಶಿಪ್ ಏನೋ ಸಮಥಿಂಗ್ ಇಸ್ ದೇರ್, ರೈಟ್?
ಇಲ್ಲ, ಪ್ರಿನ್ಸಿಪಲ್ ಅಂಡ್ ಸರ್
ಇಲ್ಲ, ಏನೋ ಚಾರ್ಜ್ ಕೊಟ್ರು ಅನ್ನೋಗಿದೆ. ಪ್ರಿನ್ಸಿಪಲ್ ಕೊಟ್ರಲ್ಲ ಸರ್?
ಇಲ್ಲ, ನಾನು ಇಲ್ಲ, ಈಗ ನಾನು 15 days ಆಯ್ತು ಇವಾಗ. ಅದನ್ನ ಹೇಳಿದ್ದು ನಾನು, ಊರೆಲ್ಲ ಸುತ್ತಿ ಮತ್ತೆ ಇಲ್ಲ ಬಂದದ್ದು ಅಂತ. ಸಾಕು, ಎನಫ್ ಅಂತ.
ಹೌದು.
ಐ ಕಾಲ್ಡ್ ಇಟ್ ಆಫ್, ಸಾಕು.
ಈಗ ಏನು 60 ಹೆಚ್ಚಾಯ್ತಾ ವಯಸ್ಸು, ಏಜು?
ಇನ್ನೊಂದ ಕೆಲವೇ ತಿಂಗಳುಗಳು.
ಕೆಲವೇ ತಿಂಗಳು. ಸೊ ಸ್ಟೆಪ್ಪಿಂಗ್ ಇಂಟು 61 ಸೀನಿಯರ್ ಸಿಟಿಸನ್ ಬಂದ್ಬಿಡ್ತೀರಿ.
ಸಾಕಲ್ವ ಗುರು?
ಸಾಕು ಸರ್, ಒಳ್ಳೆ ಸರ್ವಿಸ್ ಕೊಡ್ತೀವಿ.
ಇನ್ನೇನಾರು ಅದಾಗಿದ್ದದ್ ಬಂತು ಅಂದ್ರೆ ಬೋನಸ್ ಅಷ್ಟೇ, ನಾನಂತೂ ಹುಡುಕೊಂಡು ಹೋಗಲ್ಲ.
ಸಾಕು, ಗಿವನ್ ಎ ಬೆಸ್ಟ್ ಸರ್ವಿಸ್.
ಸಾಕು ಏನೋ.
ಎಲ್ಲ ಟೆನ್ಷನ್ ಲೈಫ್ ಸರ್ ಅದು.
ಬಹಳ ಕಷ್ಟ ಅದು ಈಗ, ಎಸ್ಪೆಷಲಿ ಡ್ಯೂರಿಂಗ್ ಕೋವಿಡ್ ಟೈಮ್ಸ್.
ಹೌದು.
Life is, administration and satisfying all the people is the most horrible thing. Now academicians we are misfit actually, very difficult.
ಹೌದು.
And the type of administrators coming is not easy to manage them. Anyway, it's a great time. So let us spend few minutes with all our students, silly faculty. So 1 minute left. Okay.
ಎಷ್ಟೊತ್ತಿಗೆ? 11:30
11:30 to
1 o'clock.
Yes, sir. Hello, sir. Wait.
I have to start.
Shall we start, sir?
Yeah, please.
Yes.
Welcome back, participants. We shall now resume our session. Before we begin with the session, I shall first introduce the speaker of the session, Dr. T.N. Nagbhushan. We are happy and proud to have with us Dr. T.N. Nagbhushan, one of the eminent administrator, researcher, and well-known outspoken personality. Dr. T.N. Nagbhushan is currently working as principal of SJ College of Engineering, Mysuru, and Dean of JSS Science and Technology University, Mysuru. He obtained his ME in Electrical Engineering and PhD in Neural Computing, both from Indian Institute of Science, Bangalore. He is having over 36 years of teaching, research, and industry experience. He also worked as a General Manager, Microtech Tel India, Mysuru, Engineering Manager at Aspire Communications Private Limited, Mysuru, Special Officer, VTU E-Learning Center, Mysuru, and Chief Executive Officer, JSS Research Foundation. His academic and administrative merits made him to shortlist in the final 3-member list for the position of Director of Indian Institute of Information Technology, IIIT, Dharwad in 2017. Professor Nagbhushan successfully guided 9 candidates towards doctoral degree and 70+ publications in reputed journals. Delivered several lectures in national and international conferences and workshops, including keynote addresses in many conferences. He is a reviewer of many journals and conferences of high reputation and working as a consultant to many industries. He was awarded Best Engineering Professional by International Biographical Centre, Cambridge, UK during 2010 and delivered convocation address at Oxford Engineering College, Trichy. He has organized 2 international conferences and worked as a general chair during 2015 and 2016. He served as a board member and technical expert in several advisory boards of both government and private agencies. Professor Nagbhushan is invited by several international universities or institutions to deliver lectures and for various assignments. A few of them are OCO Graduate School of Venture, Seoul, Korea, University Technology, Mauritius, Hanan University, Osaka, Japan, IEEE International Conference, ICICI, Singapore, Sun Microsystems, San Francisco, USA, Georgia Institute of Technology, Atlanta, USA, Mauritius Research Council, Mauritius, Durban University of Technology, Durban, South Africa, Nokia Corporation, Finland, Aalto University, Helsinki, Finland, St. Petersburg Electrotechnical University, Russia. Professor Nagbhushan is the key person responsible for establishing Multimedia Lab, established Nokia Lab, developed IoT and Big Data laboratories, built a good team of faculties and elevated the reputation of the institute, conducted ISTE or AICTE funded STPs, responsible for transmission of high quality live transmission lectures through EduSat, succeeded in live transmission of video lectures of Indo-US Relation Leadership Institute from Infosys Mysore campus for the whole nation through EduSat. He could secure grants to the tune of rupees 70 lakhs to generate 7 quadrant material under NMEICT MHRD project for VTU e-learning to develop course materials. He is responsible for developing a new technology for generating course materials which involve 3D animations with least storage. He was quoted to work in a specific range of cell phones during 2010. He is the first to develop the 3D animation rich course over mobile phones in 2010. Developed new laboratories such as CAD Lab, eYantra Lab, Nokia Microsoft Lab, set up training centers for NDA experts, evaluators, and created state-of-the-art gigabit media LAN across the campus, and the campus was made fully Wi-Fi to enable e-learning. Overall, it is needless to mention that the JSS Research Foundation witnessed vertical growth and accounted for a good number of research publications. His accomplishment at both academic, research, and administrative levels are innumerable, and the list goes on. He is very kind-hearted and accepted our invitation amidst his busy administrative schedule, and we wholeheartedly welcome Professor T.N. Nagbhushan to deliver a lecture on principles of neural network in this training program. I wholeheartedly welcome you, sir.
Thank you very much. I think very huge introduction. I requested Sharmila Kumari to cut down to only few sentences. Thank you very much. And actually, I don't know whether I really deserve so much or not. Anyway, thank you very much, and I will start actually sharing my plan as follows.
Yes, sir. It's visible, sir.
Yes, yes.
Is it visible?
Yes, sir.
Yeah, okay. So thank you very much. During the next 60 minutes, I will be talking about the neural networks in a different way. Actually, most of you have read the textbooks, but I try to give the inputs, though it is very old one. Actually, it is not actually new neural networks. We started actually using neural networks in early 1986, 87. So when I was doing master's degree at IISc, we actually started learning neural networks and started coding during that time. Now a lot of time has gone in now, but still many people do not understand, and still people use it only as a black box. But as engineers, we need to understand the neural network from mathematical point of view. So therefore, I try to give a lot of importance to the understanding of neural networks from mathematics point of view, so that you can start really looking at the neural networks from different perspectives. And anyway, the neural networks are available in a much more enhanced versions. A lot of developments have taken place now, and during this era of pandemic, deep learning architectures and other neural network models are being extensively used. So a lot of time has gone in for the development of such architectures. So I was told that we need to give very elementary foundations to those people who are participating for the first time here in neural networks. So therefore, I try to give as much as possible in a very compact way, so that you should be able to understand the neural networks, which is slightly different from what actually you're seeing from textbooks. So my presentation, because the neural networks are fed by data. Dr. Guru has spent a lot of time in the morning giving you the foundations on features, feature extraction, feature selections, and so on. So those things are very important here. I also touch base with some of them and want to give that from linear algebra point of view. So therefore, you can ask questions related to that. So some foundations I want to tell you about the data, vectors, patterns from linear algebra perspective, because this is very, very important, because we need to take these input as a data to the neural network, and this data basically is a kind of a vector. And we need to really look at this most important thing, that everything that we are seeing is basically to be seen as set of points in space. So the input that we are giving, or the features that you are considering from wide varieties of problems, need to be seen as a set of points in that dimension space. So that gives you a lot of idea about the working of neural network architectures, why actually they are performing classification and so on. Then I need to start with a very basic, perceptron. Its mathematical model, how actually the simple neuron has been developed, and how actually it has been used, and what kind of problems that it is going to solve. So concept of linear separability. Then comes actual limitations of perceptrons led to the development of multi-layer perceptrons with more hidden layers. And we need to spend time here on the mathematical foundations. So how actually this learning takes place, how the error propagation basically happens, and why actually it classifies the input data into different categories and so on. So this mathematical touch is important. And then comes another type of popular neural network, now not actually extensively used after deep learning. It's called radial basis function. And how actually this is seen as a curve fitting in a multidimensional space. And of course, we have these actually are taught under supervised learning. Under unsupervised learning, we have self-organizing maps, SOFM, developed by Tao Kohonen. The last part is I touch base with some basic data about the deep learning, because it is going to be discussed extensively tomorrow. Some applications. This is how actually it goes. Now the source of all these kind of neural computing and everything machine learning that we are talking about is basically inspired by the human brain. Now all of you know that some of these statements that I'm making, all of you are familiar with this, but it's kind of a recapitulation. So we are all humans, and therefore input to all of us basically is a kind of a continuous signal or analog signal. Example, the speech is a continuous signal over an interval of time, and even the image or the video that we are seeing basically is a continuous signal over an interval of time. So therefore all living beings basically operate on the continuous signal. So therefore there is a kind of variation of amplitude with respect to time. So that's the kind of a graph in 2D that you can see. This is a kind of an analog computer, human brain. And it uses continuous signals, as I told you. So sound, noise, speech, songs, etc., video. So these are all dynamic media, so time-dependent data. And so it's needless to say that all living beings like birds or animals and all these living beings basically use continuous signals for an interval of time. And they are being fed to the brain, and the brain receives these continuous signals and process the signals and act according to the requirements. Now we are trying to do something different here. Now how to really emulate the same kind of characteristics on a different continuous system? Like a digital computer, it cannot take continuous signal. Therefore we need to go for discrete samples, and then use the discrete samples for digitization. So continuous signals, the humans are extraordinarily capable of cleaning the unwanted contents received from the input space. That means, if a noise is there, if I am here, speaking now, if there is a fan noise, the human ear is capable of ignoring that noise and therefore take only the basic, signal, fundamental signal for processing. So this is something, extraordinary capability of the brain. So that means it is immune to noise. This is one of the important thing. And this important thing that we need to give to the neural network also. That means this should be able to remove the noise and also should be able to generalize. This is very important concept. So machine learning is synonymously used basically for neural computing, artificial neural networks. All these things have started in the beginning. And now that everyone talks about machine learning basically uses the approaches that are developed as an outgrowth of the algorithms and architectures on neural networks. So therefore machines could be any kind of device now, like your smartphones, and machine learning depends on the data that is fed into it. So that means what kind of data that we are going to give to the smartphones or any kind of device determines the quality of the output. So therefore, the algorithms that are used to train these machine learning, devices, are very critical. So therefore, what kind of algorithms are used? And of course, all these algorithms are heavily based on mathematics. So therefore, mathematics is very, very important in all these cases. So machine learning deals with everything that attempts to make machines smarter and even intelligent. So when we talk about the machines, smart machines and intelligent machines, so make the machines solve problems in a way similar to the human brain. I don't say same, but in some approach it has to be similar. And machine understanding of text, audio, image, video, they're all open areas for advanced research. So how basically machine can understand the text, audio. So a lot of research is going on around the world. And now thanks to the deep learning architectures, which are quite capable of taking large amount of data and processing it in a relatively short duration of time. So one of the important thing that even the AI, when people talk about AI-based machines, I don't really understand whether the AI-based machines are able to give reasoning for its decision that is taken, like a human brain. So for example, we learn certain paragraphs, a comprehension, a question is asked, then we will tell an answer. Then if there's a counter question that how did you arrive at it, we always give an answer to that. So that kind of a capability is called reasoning. And the neural networks cannot give any kind of reasoning. They simply take the input and gives the output based on the generalization capability, whatever it has learned. It gives a closest output, which is quite good enough for our management. So, but reasoning is something which is missing, and that's an open area of research for all. Generation of clean data to be given to any machine learning algorithm itself is a vast area of research. This is what exactly Dr. Guru has really spoken about, the features and feature extraction, feature reduction. So much of volumes of work has really gone in because clean data need to be given in order to make the machine learn and even make it smarter. So the problem is that, because neural networks, if you see right now as a black box, you need to give the data. So what is this data? This data is basically the data that you are taking from your domain, problem domain. You are trying to solve a problem, and you should have the knowledge to extract the data from the given problem. And therefore, such data need to be represented in appropriate form. So what is this data is all about? So before one apply machine learning algorithm to solve a problem, there is a need for sound understanding of the data representation that best describes the problem. So I use the word best describes the problem. So that means you can have infinite number of data samples possible for a given problem, but can you collect all of them? Or you can collect only some significant features from the vast data. So a lot of algorithms are discussed in the morning. So this is one of the important things. So data is basically the thing, but the features that we are talking from pattern recognition point of view. So when we want to classify certain things, we need to extract the features that best describes the given object. So how to get it? So this basically requires the user, to have a sound understanding, and he has the freedom to choose what kind of data that he wants. So how many features that you need to choose? So this basically it has got high impact on the learning capability and also efficiency of the architecture of the neural network that you are trying to use. One of the things is that curse of dimensionality. So that means if we increase the dimension, if we increase the total number of patterns, how it is really going to increase the space? Because ultimately, when we want to perform certain classification to a given problem, so neural networks are best suited for classification initially. They can also be used for association, and also they can be used for optimization, and so many things are possible with neural networks. So to understand this in a very simple way, you want to classify the data into 2 classes or 3 classes, then it is possible that you need to consider that data and how many such data samples are possible, how many features that you can really take, is one of the important thing. Now let's take, for example, we want to classify the dogs. Now what are the features that we can take? For example, I always take the color of a dog and height of a dog. So there are, say, dozens of dogs available, and for each of the dog we take a color and also height. So we want to classify the dogs into different categories based on 2 categories. So what kind of species the dog belongs to. Now, the two categories are not enough, so therefore I will go for a third category. Suppose I measure the leg size also, another feature. So then I can also go for 4 parameters like color, height, leg, and eye color. So like this, you can keep on adding more and more prominent features that you really want to take. And these actually are measurable parameters. And therefore, with all these kind of parameters that you're accumulating, you want to classify the dogs into different categories. So this is a very simple problem and visible problem. So therefore, you can always do that. Okay, so therefore I give the name mathematically x1, x2, x3, xn up to xn, n number of features that you can always take for the category of dogs. So similarly, this can be applied to any kind of problem. So x1 to xn is n number of features that you can always measure, and how many such features that you want to measure determines, say for example, n number of features. The challenge is now is to classify the cats and dogs in the world. So that means I have two categories. I measure the cat and dog by with these parameters: color, height, leg size, and eye color, etc. And want to classify them into two categories. So that means there are n number of features possible, but I will not be able to take all n number of features for these categories. And therefore, how to do this? Now, the patterns that you want to represent here, use a very simple thing. Now, if you take only one feature, for example, you take only one color. So that means I always, use only one feature. So this one feature, you can see that you can represent this feature on a single line. Okay, suppose if I take two features, feature 1 and feature 2, it forms basically a plane on which this, cat and dog are placed. So that means if you start searching from beginning, for example, here, and you want to identify whether a cat, dog, and so on, you can classify them into two categories. It is easy and less time consuming because you are bound to really identify them and so on and categorize them. So there's no problem. But when you actually increase the number of features to 2, so you can see that you need to start from line 1 and identify which category, go to line 2, line 3, line 4, line 5. So you have to exhaust all the space here. So the search space basically increases now here with 2 features. How about going for the next one now? So if you want to classify, you can see that this is how you're going to classify. That means when you search, this forms one class, this another class, another class. Okay. Now, suppose if you want to go for 3 number of features, for example, so that means I go for a kind of a cube here where you can see that the cats and dogs are placed with 3 important parameters like leg, color, the height, and so on. So that means this is how basically looks like conceptually. So with 3 features, actually, you see that automatically the entire space is now to be searched here. So you take the top of this cone. So this forms the first, plane. You go from one, etc., one line to next line and so on. So, sorry. One second. Okay, so when you go for this selection here, you can see that the search space increases because in this cube you can see that there are number of planes which are stacked one by one. So plane 1, plane 2, plane 3, plane 4, like that. So on each plane you need to identify whether the cat exists or dog exists. Then only you can always form a region. So that means the search space now increases considerably, starting from 1 dimension to 2 dimension to 3 dimension. So you can see that in this picture the classification region is possible and search space basically increases. This is one of the important thing, that you cannot really take a large number of features, because when you increase that number of features, the search space also increases and the patterns becomes sparse. So that means the positioning of features in the pattern space need to be understood with highest clarity. This is very important. So even though neural networks in the beginning, in the early 1980s, people were not aware, they used to take all kind of data, all kind of features, try to feed them and say that my network is working better than that and so on. But with more and more knowledge actually getting into the feed here, people started identifying that you need to have only good features. You need to have reduced features because you do not want large search space, which is time consuming. And second thing is that you need to pick up only significant features, which best describes the problem. So this is one of the important things, that everyone should be able to understand in neural computing area. So a must for everyone. So the data having n features appear as a point in the n-dimensional space. So this is where I want to stress that the features that we are going to reduce from n dimension to discrete k dimension. So each feature, see, set of features, I use the word set of features, forms basically a vector. So a vector in n dimension space and a vector in k dimension space. K can be 2, 3, 4, etc. So that means when you reduce from n dimension to k dimension, the search space increases, and therefore the total number of samples that you want to take, even though if they are not many, you should be able to get a approximately better classification in accuracy. So the greatest challenge is to ensure how reduced features generate reverse mapping. So that means I reduce from n dimension to discrete 3 dimension, then I want to reverse it map. I should be able to really pinpoint into that. So how actually this can be done? Usually genetic algorithm does this kind of work. From binary coded genetic algorithm, we should be able to do this kind of reverse mapping. And for example, you take a brain image. So you take Alzheimer's disease. So you have the highest, you have the brain image, and you have the data, which is a very high dimensional data because of the white matter. So you need to have a feature reduction. So genetic algorithm can be used. You can use neural network for training. And once it is identified, you can always go back to reverse mapping also. So summary about this data is that data must be clearly defined for the problem and must capture the significant characteristics. Data has many features which decides the dimensionality. Number of data samples could be restricted or available in plenty, subjected to research topic. And each data sample is to be seen as a point in that dimension space. And all data samples are thus seen as points in that dimension space. And everything like text, audio, image, video can be represented as points in space. So this is the beauty. So neural network basically takes the input. Input is a vector, and vector is basically composed of numbers only. So that means whatever problem that you are trying to solve, it is basically you are feeding a vector as input, a set of vectors as input, and the algorithm learns and gives kind of an output. So what kind of data that you are giving? Some mathematical point of view, it is basically a number that I am feeding to the black box. So this vector that you are deriving from text, you are deriving from your audio signal, audio speech, or a music, or an image, or it can be sequence of frames constituting video. So that means I should be able to represent everything in the world with these multimedia data. So some are static, some are dynamic here. The dynamic is audio and video are dynamic, and whereas text and image are static. So therefore, every problem that you are talking about, once you have the features, these features are nothing but vectors in the space, and these vectors obviously they are point in that dimension space. Therefore, the segregation of these points depicts some kind of a behavior, statistical dependency between one point to another point exists in that dimension space, for which these neural networks are amazingly best suited to understand the position of these points in that space through a learning. So this is something you need to really understand afresh. So there exists a wide variation in the way that data samples are acquired. And for example, face recognition, each facial image is taken as a matrix, and assuming that we can cascade all the rows, we have one single vector of the image which is a point in the dimension space. For example, if you take 1 megapixel camera, 1 megapixel resolution, and 1024 into 1024, so that means you can cascade each row 1024, next 1024, and so on. So one single, that large single dimension vector, it belongs to that dimension space, or 1024 into 1024 dimension space. It's a point actually. So if you take another image of the same person from different angle and so on, it is another point in that space. So that means person having similarity, the points basically lie very closer in the dimension space if the input features are not too different. Several such samples define the points at different positions in the vector space. So the vector space in this example define the space of vectors that represent the faces here in this case. So after ensuring that we have defined all the data samples as vectors in that space, the operations performed on the vectors inflict changes in the vector space. This is very important. Suppose if I take a 3D, so suppose I have A1, B1, and C1 as 3 points in the space, 3 operators in the space, and this becomes a point because A, B, C, if I take as a set here, each one of them belongs to X, Y, and Z. So therefore, it belongs to one point in the 3-dimensional space. Okay. So therefore, I can always join this point with respect to the origin. So therefore, it has a magnitude and direction. So this qualifies as a vector. So this incidentally, this also a feature for some kind of a problem. Only 3 features. Like for example, if you take iris, it has 4 iris data. It has 4 features. Now I take it up one data. I will take it off one feature, reducing it to only 3. So therefore, I can always represent it and plot all these 150 features of iris flower inside a cube, 3-dimensional cube, and see how the data points are scattered. Okay. So therefore, the operations that I am going to perform, for example, if that point is there, I can multiply that point by a scalar and push that point to some other, position in the same space. I can always take the data, and I can always, that data belonging to one plane, I can always project that point into another plane in the same space for various operations. So that means whatever addition, multiplication, and whatever De Morgan's theorem that are applicable here, so will always be applicable to these vectors, and therefore the features that we can always play with the features in the space, which is going to really help us a lot actually in making the neural network understand better. So the data samples are often subjected to a lot of pre-processing before using them as input to machine learning algorithms. So this is what basically deduction and all these things are about. So algorithms to refine the raw data and pick the significant data, so is one of the important thing, and run through the dimension reduction process to ensure that data captured in lower dimension are more meaningful for the task. For recent research in this area, you can always do a Scopus search for the top 10 people who have been doing in this kind of work and high impact publications on data reductions, how to really obtain most significant features. You always have n features, but which algorithm gives you the most significant feature and how many such features that are needed. So this is the main important task that one need to really do before you start using any kind of neural network. So therefore, I am just trying to establish the foundation that when you want to use neural network, the people coming from non-circuit branches, they don't really care about how the neural network architecture really works. But people in the electrical sciences division, computer science, and so on, they need to understand the working architecture, because these are the people who are going to build newer algorithms, improved algorithms. And if there is a question that my neural network gave a better answer than the previous one, which is published in the research article, I should be able to give a reason why. But most of the theses don't give this kind of answers. If I don't give an answer why actually my algorithm gives a good result or improved result, then for which that I am asking for my PhD. So that's most important. So therefore, in order to do that, one need to know the top 10 people, at least 10 people who are working in this area, whose credible publications need to be compared with our work in order to make sure that we are also going in the right direction. So now the pattern space is the feature space. So for example, I take xi11, xi12, xi13, xi1 is one single vector. This one matrix, one feature. So this another feature. So like that, I have n number of features here. So each feature has each sample here. Say pattern 1, I call it as a pattern 1, n features, pattern 2, n features, and so on. Pattern n features. So for a typical problem, general problem, I have n features and n such samples. My job is to really use this as an input to the neural network, a black box, and want to train it so that it can understand the internal representation and gives an output which is actually expected, which I'm also familiar in a supervised learning. So each row is a vector and has n features, and each column is also a vector and has n features. So this is how basically the entire data need to be prepared and kept actually. So the input output vector for a typical problem. So I call it as mu as a problem pattern, pattern 1, mu1, pattern 2, mu2, and mu n is n such of n patterns. And each pattern has n features, xi11, xi12, xi1n, xi21, etc., xi2n, etc., and xin1 to xinn. So this is the input. And the output is basically kind of a class or a label that I am trying to do. So how many classes I have? I call zeta 1, zeta 2, zeta k. K can be 2, 3, 4, depending on the kind of problem that you are going to solve. So essentially, this data preparation is the initial task. You should be very, very clear about the data and how it is obtained, significant patterns, number of classes, and number of such patterns you need to really prepare. This is most important thing. You should have a good understanding about this for any given problem that you are going to solve. So this basically comes under supervised learning system because you have the input data and also output data. So if you look into this now, the input data is a vector, the output is also a vector. So both input output are vectors. So pattern 1 comprises of input vector and output vector, pattern 2 input vector and output vector of respective dimensions. Now, the input to the neural networks are static vectors in the input space because they are static because they are derived from the features and features don't change because you are fixing the features. So therefore, they are all static vectors in the space. One can plot these inputs in the respective spaces. Suppose you can always plot this and visualize how they look like in 2D and 3D. Okay, but in higher dimension you cannot do. You can do dimension reduction and see the scattering of these points actually in the 2D and 3D to understand whether there is some kind of statistical dependency among the pattern vectors or not. So that can also be done. So these points may belong to different classes and there could be some kind of a overlap also. So this is another important thing. So these points which are distributed in the space may be linearly separable or non-linearly separable. This is something, in linear algebra, you need to understand linearly separable and non-linearly separable. Suppose if the points are there in the input data, and if the points basically are scattered, if you're able to separate them into two regions by a straight line, in case of 2D, in case of 3D by a plane, the plane is again made up of straight lines, okay, at the boundary, or in a multidimensional plane, hyperplane, separate this into two categories. So then the points are said to be linearly separable. So if the points are not linearly separable, means there is an overlap. So the classes are scattered and mixed together, then obviously you cannot use a single line to separate them into two categories and so on. So therefore they are non-linearly separable. So therefore the problems which are linearly separable are easy to solve, and problems which are non-linearly separable, it's difficult. So that is the one which actually put the neural computing, which picked up from 1960, into a complete halt till 1986 when Hinton and others discovered the famous multilayer perceptrons. So solutions to these classification problems attempt to solve to different boundaries so as to separate the inputs into different classes. So therefore, the input-output vectors that when we plot here, so the points need to be linearly separable for a very quick convergence, easy and fastest. If the problems are not linearly separable, patterns are different, then you need to really look at more complex architectures, neural network architectures to solve such kind of problems. So any data arising out of image, text, voice, etc. are ultimately vectors in that defined space. And all operations on the vectors do inflict changes in the respective data in that dimension space. The learning process. Now we basically look at two types of learning, even though there are other kinds of learning like reinforcement learning. I won't touch all of them. I look into more common applications that most computer science people will be doing is supervised learning, and I also touch upon unsupervised learning. Okay, these are two different categories. So perceptrons were actually developed by McCullough and his student, Pitts, both of them from MIT. And multilayer perceptrons were discovered by Hinton, Sednowski from University of Toronto. Radial basis functions actually developed by Moody and Darkin in early 1980s. And coherence self-organizing feature map is exclusively only architecture available today on unsupervised learning. So now that we have Hinton and others basically are responsible for developing deep learning architecture, which is the current architecture now. Okay, so we need to really look at the mathematical way of looking at the supervised learning. How actually we can look at the mathematical perspective. So that means you have a black box, and whatever happens internally, I call it as phi. You are giving set of input vectors and want to get set of output vectors. For every input vector, you want to get an output vector. This is the philosophy of supervised learning. In a very simple way, in a layman's language, you give a vector. A vector can be n dimension or whatever dimension that you are already collected for the given problem. And now you have the output vector. Labels are also known to you. You give the first vector and do some kind of learning. This phi does that kind of a job and produces an output. Gives the next vector, produces the output, and give the next vector, and so on. So this iterative process will continue. And this is what we call it as supervised learning. So that means I have xi mu. That means mu is equal to patterns. Pattern number 1, 1 to n. Mu is equal to 1 to n. And xi is an n-dimensional vector. So therefore, it belongs to n-dimensional real space. So that means whatever data that I have shown you, I have shown that as, xi is basically a vector, okay, in a n-dimensional real space. And there are such, 1 to n such vectors exist. And this basically phi is the mapping. And what I want is basically an output vector O mu that belongs to discrete k-dimensional space. The input pattern is n dimension and output data is k dimension. And this phi basically does kind of mapping. So that means you are mapping vectors from one dimension, okay, and to another dimension. It is not just a mapping, but it is basically a learning. So that means what you are trying to do is that you are trying to understand the position of these vectors in the space, okay, mu, and also you are trying to map them, projecting them from one dimension to another dimension. And in the meantime, you also understand where actually it is mapping. So this is something very important. This phi is basically the neural network architecture that you are trying, and also the algorithm that really defines what actually this phi does. This is very important thing. So supervised learning is a very simple equation. Xi mu belonging to Rn maps through phi to an output O mu that belongs to discrete k-dimensional space Rk. Now, this is the first, mathematical model of a biological neuron. And in biological neuron, I didn't really go for that. Let me just, give you the input here. So, in between, I'll just try to toggle it. Please bear it. Is this visible?
Yes, sir.
Okay. Okay. So suppose if I look into this discrete k-dimensional space. So you have the biological, most of you have seen it, just only for sake of clarity that I am writing here. So this axon, arborizations and so on. This another neuron that I am trying to write here. Okay. And this, so this point where these two touches is called the synaptic junction. So whenever the neuron basically fires, the signal flows and there is a chemical deposited. The strength of the chemical determines the weight actually that we are trying to do that. So that means this is neuron 1, input 1 and input 2. And therefore we have the weight that W is basically called synaptic weight W. So the Hebb's postulate, Donald Hebb actually told that he postulated that whenever the neuron fires, there is an increase in the strength of the chemical that attributes to learning. So it's also set of memory and also set of recall. So therefore, whenever we learn, the strength is increased. So this part is basically captured as a set of input X1, and this W is multiplied by this one to produce a required kind of an output. So therefore, the number of inputs are coming here, and the threshold is taken, passes through a nonlinear function, and the entire W keeps changing here, because in a biological sense, the strength of the signal keeps increasing. And this is what basically is controlled in case of the McClelland-Pitts model of this neuron here. So the mathematical model for this neuron is a very simple one, where the inputs are basically Xi1, Xi2, Xi3, three inputs. And this neuron is basically a summation, linear is kind of a summation here. The synaptic weights are called as WJ1 because this jth neuron, first input WJ1. This script is also very important here while writing program. And this WJ2 and WJ3 and WJN, etc. So what it does is that it multiplies as the input Xi1 WJ1 plus Xi2 WJ2, etc. plus Xi WJ. That's the input to this neuron. So that means it basically does a linear summation of the input, and it passes through a nonlinear activation function G, and it produces an output depending on this G. This G can be a threshold. If the total input is more than the threshold, this sends a signal 1. Otherwise, it sends a signal 0. A very simple idea captured from biological neurons. And this is basically termed as a perceptron. So a single perceptron consists of a very simple model where you have the inputs taken from your problem, and these W's are initially randomly selected, and you take the linear summation, pass through a nonlinear activation function, produce an output. If the output is not correct, again you make the changes in the W such that WJ1 is equal to WJ1 old plus delta WJ1. So some delta J is basically added to this. So like that, you're going to change this W until this Xi11, Xi2, Xin produces the required output. And this is basically the complete learning algorithm for a particular perceptron. So several such neurons were joined to form a single network, and this is called as a perceptron network. So here you have 6 inputs and 3 neurons. And what you can see here is that you can see that the total input. This is 3 neurons and 6 input. So therefore, every input here Xi1 is fed to all the 3 neurons. So every input is distributed to this. Every input is distributed. This is a beauty. And now you can see O1, O2, O3. So these are respective outputs. So if you have taken some n number of samples like this, 6-dimension space points, and you're trying to map it to 3-dimension, if the patterns are linearly separable, then the perceptron learning algorithm converges in finite number of iterations. Now this perceptron network works exceedingly well, very well actually, if the patterns are linearly separable in the input space. Now this theta is actually in extra dimension here. I can call it as Xi0 and call it, the weight actually is fixed as -1. And therefore every neuron, you can see that this theta is basically seen as a bias. Now, one of the important things that you need to understand here is that the input to this neuron is a summation of Xi1 W11, okay, Xi2 into W12, Xi3 into W13, etc. What is this basically? This is basically an equation of a straight line, okay, y is equal to mx. And this theta is basically bias. So that means it is of the form y is equal to mx minus c, plus minus y is equal to mx plus c, or y is equal to mx minus c. So that means I am changing this w. So that means I am giving each one of these inputs basically is treated as a line. Okay. So 1, 2, 3, 4, 5, 6 lines are fed to this particular neuron. And these input, geometrical, you can see that these 6 lines basically forms a convex hull in the input space. This convex hull can be closed or convex hull can be open. Okay, so that means the changing of this w's basically and changing this theta changes the orientation, okay, of the convex hull in the input space. Incidentally, these convex hulls are arbitrary classification regions in the input space. So that means taking the Q into the linear algebra, the points which are scattered, okay, I am generating the boundary, okay, which are controlled by various straight lines. These straight lines basically are hyperplanes in a higher dimension space. So these these lines basically constitute hyperplanes, and these hyperplanes, develop the region between the patterns belonging to one class to patterns belonging to other respective classes. This is the beauty of the perceptron learning network, and also multi-layer perceptron, and all supervised learning neural networks, that uses the optimization, quadratic optimization. Basically, they perform these kind of operations. So what we understand here is that vector matrix multiplication. So if you go to the previous slide here, this entire thing is basically a vector, and this WJK is a matrix. So therefore, I am multiplying the vector into matrix and producing another vector here. So net input a neuron is set of straight lines. They form convexels, and output neurons from an arbitrary classification boundary. And boundaries are found by the hyperplanes, and hyperplanes can classify only if the input patterns are linearly separable. Simple perceptrons can only solve linearly separable problems. So for example, you take a very simple AND gate and OR gate, but it fails on XOR gate. It's a well-known theory in neural computing. So the multi-layer perceptrons actually were discovered because the patterns in all problems are not linearly separable in the input space. So therefore, we have the patterns which are non-linearly separable. So it's usually most of the problems that we deal have patterns which are having overlapping of classes. Therefore, you cannot really use straight lines and hyperplanes to classify very easily. It's very complex. So the neural network research came to a halt because Withrow from MIT showed that an XOR problem cannot be solved by this perceptron. So bringing the entire research into halt. So it took almost 16 to 20 years to develop an algorithm for a multi-layer perceptron. People knew that they can add one more layer of neuron, but they didn't understand how to develop an algorithm which will train the weight matrix such that the input can be mapped to the respective output, and also they should be able to classify the patterns which are non-linearly separable. So therefore, combination of many hyperplanes enclose non-linearly separable patterns, and therefore generating complex nonlinear boundaries in the input space. This is the idea which actually developed by Rummel, Hart, Hinton, Williams, and Sednowski in 1986, and is one of the seminal paper on error propagation in feed-forward neural networks in 1986. So the typical architecture of a multi-layer perceptron looks like this: input 1, input 2, and you have several layers here. So a typical problem is that 150 neurons and 250 neurons in the hidden layer. Input layer is 150 dimension, output layer is 16, and so on. So this is another typical, the backpropagation network here: input layer, hidden layer, and so on. And this is I used to teach this in terms of all mathematics, like the entire learning algorithm can be understood in terms of all partial differential equations that you need to derive from input to output. So I will show you some of them here. Okay, so you take for example, 3 input and 2 output with 4 hidden neurons for a typical multi-layer perceptron. So I call it as Xi1, Xi2, Xi3 as the input, and these 4 neurons are arbitrarily selected. Output is only 2 neurons here, O1 and O2, and I call it as layer I, layer J, layer K for sake of clarity, and assume that I have n number of patterns, mu is equal to 1, 2 up to n. So if you look into this, the net input received by every neuron is multiplication of the weight matrix WJK into Xi11, okay, and W Xi2 into W JK W21, and Xi3 into W 13, and so on. So this HK mu, this net input received by every neuron, K is equal to WJK into Xk. So this basically is a linear summation. So each neuron, okay, for every neuron, this is the input. And the output of this neuron is Vj mu. The output of this neuron is Vj mu. So when I pass this to a function G, of HK mu, I am going to get an output here. And then this Wij is the weight matrix, Wjk is the weight matrix here, initially random. And the output, the net input received by this Hi mu is a linear summation of Wij into Vj mu. Vj mu is the output of this. The training pairs are Xi mu and zeta n, okay, zeta x or k. So consider the net input received by each neuron, Hk mu. This is the net input received by every neuron, okay. So this is nothing but Xi11, W1, as I told you, the equation of a straight line, Xi2, W21, and so on. So output of each neuron, Vj mu, is equal to G of Hk mu. So G is an activation function. So I can always substitute for Hk mu. You are going to get this. So net input received by this neuron, Hj mu, is again, net input is a vector, matrix vector multiplication. This Vj mu I am substituting, it gets embedded. So the output is nothing but O is G of Hj mu ultimately. So if you substitute for all these things, now you are going to get the output, which is actually, consisting of a function embedded inside another function. G is actually the function that we are taking. Now the output is basically, is to be compared with respect to the desired output. So zeta mu is known to me. The computed one is Y mu. So I take this as a quadratic error. I form a quadratic function and I want to minimize the quadratic function. This is the beauty. So if you look into the optimization of the optimization problems in engineering and technology, you see that this can be solved easily by a calculus-based methods. So I want to minimize the error. So therefore, I can use any calculus-based methods can be used to solve this problem here. So putting all these equations inside this, the objective is that I want to minimize the error. So therefore, I take the partial derivative, this error with respect to the Wij, first one which is embedded inside, and then equate it to 0 because I want to minimize this and get Wij is equal to this. And this I call it as the entire thing after this. The beauty is that when you take this function, it becomes G dash, because when you differentiate with respect to the dependent variable, you are going to get G as a G dash. The beauty is that when you use an activation function, you cannot really, take this first order equation, differential equation. If you want to solve it, you need to go for either Newton-Raphson or any other numerical methods. But if you choose a function which gives the derivative by itself, okay, so that's the beauty. So this G is a sigmoidal activation function. And the beauty is that the G dash here, G dash is equal to G into 1 minus G. So when you differentiate and solve this problem, the G dash I put, this is missing here. So G dash is equal to G into 1 minus G. So directly you can substitute here without actually going for any numerical method. That's the beauty. And incidentally, this activation function is smooth and continuous. So therefore, you can differentiate at a very close to every point here. That's the beauty. Okay. And therefore, the Wij new is equal to Wij old plus delta Wij is the new update in the weight vector. Similarly, you need to update the weight vectors Wjk between hidden and input layer. By this approximation, you are going to get two important things. One is delta I mu, delta J mu. So these two are called error coefficients. So when we want to really compute the weights between hidden and other layers here, okay, so when I want to compute the weight here, Wij, so I give the input vector here, this is randomly selected Wjk, randomly selected Wij, and I get an output. If the error is not actually the one which I am expecting, then I compute Wij new is equal to Wij old plus delta Wij by this reverse pass. So this delta is propagated backwards now here, and delta, the Wjk new is equal to Wjk old plus delta Wjk. So therefore, I have updated this weight matrix and this weight matrix. For every pattern that I am presenting, I calculate the error, I update this weight matrix here, and again present the pattern, check the error, update this weight matrix, this matrix, and so on. Friends, you can see that during the entire back and forth process, the forward pass and backward pass, forward pass and backward pass. Every time you are updating the entire elements of these two matrices. So you see the amount of computation that is taking place inside the machine. If the number of neurons are large, if the number of features that you're going to select are large here, so you need more number of neurons and more number of iterations. This is the one of the important thing that you need to understand as a computer scientist, that the working of this particular neural network is not so easy that as you think when you give it to the black box, but it does really lot of computational steps in between. Okay, and in the meantime, there are certain things that we need to understand. For example, the error that we are taking. For example, you are taking a three-dimensional, input and three-dimensional output here. So O1, O2, O3. So you can see that there is a error, surface generated here. So what we want is that if the patterns are linearly separable, the error surface is like a parabola. So that means you're going to start somewhere here in the entire U kind of a thing, and you start from, initial error is very high. You come down by performing what is known as a gradient descent, because all these deltas are basically derived based on the computation of first derivative or the gradient. And I am making actually gradient go down, so therefore it performs gradient descent in the error space. So therefore the ultimate objective here is to really ensure that the error basically comes down. So let me just give you one more idea here. Suppose if this is the error surface, if the patterns are linearly separable, you start from initially this point here. You perform gradient descent here and perform, come down here, check whether the error is 0. Again, come back, again check here whether the slope is 0, take the slope. And you can see that the slope becomes 0 here, first derivative. So therefore, the point of convergence. But when the patterns are not linearly separable, and for example, if the error surface is something, like this, okay, is kind of a surface, you can see that if you are starting initially because you are randomly selecting the weight, you see that you're performing gradient descent, you get caught here. This is a local minima. And you need to push again to come back and ensure that, you come down here. Okay, so somewhere the error may be minimum, or the error may be minimum at this point of time here. Okay, so therefore you can see that the error which is moving here is highly nonlinear. You can see a lot of hills and valleys here. Ultimately, I want to touch upon only the value which is the global minimum. So therefore, till such a case, I will be performing gradient descent. So many nonlinearly separable patterns have this kind of category. So therefore, we want to ensure that the weights are appropriately adjusted, and also we need to have certain mechanisms, improved mechanisms in the learning algorithm to ensure that the back propagation takes the data input properly and try to understand in finite number of iterations. So the demerits of this multi-layer perceptrons is it fits the hyperplanes in the output space, generate any kind of arbitrary classification regions made out of only straight lines. Okay. Then the number of neurons that make up the feed-forward network need to be fixed. This is one of the important thing. It's a heuristic, I guess. Demarcation boundaries is not smooth because the straight lines are used, and it takes long learning cycles depending on the number of features, which determines the input dimension and number of such patterns that you are going to feed, and the initialization of weight matrix. All these basically contribute to the convergence criteria of the multi-layer perceptron. Initially in 1986, when it was introduced, it used to take a lot of time even for small tiny problems. Now a lot of improvements were made. Several new parameters like momentum coefficient and learning rate, they were introduced, and even they also shown a dynamically constructing architecture called constructive feed-forward neural network. Okay, by Scott Foreman and others. They invented that kind of an architecture in 1980 from Carnegie Mellon, and people use this back propagation for wide varieties of problems. Even though it was very, very problematic in terms of convergence, they used to take, I have seen in IAC for small moderate problems in 1990. So to run that problem, it used the powerful machines used to take 8 to 10 hours time. So I have seen that actually, right? So now that these problems are totally taken care, but the beauty is that in the learning algorithm, the architecture is, the beauty is the points are scattered in input space, And the hyperplanes basically are generated through learning architecture, learning algorithm, and automatically they obtain the classification regions in the input space. And most beautiful thing of this supervised learning algorithm is generalization. Even if some features which you have fed, are distorted, still it is able to, pinpoint this specific class. That's the beauty. And this is the only neural network which has got that kind of a generalization capability, which resembles close to the working of the human brain. So convergence is not guaranteed. So applications are plenty here. So all these are applied for any kind of problem can be solved. So these are the problems people have attempted. Complexity, okay, Alzheimer, Parkinson, retinopathy, cancer cell detection, and so on. So this is, I think, we stop. It's at 12:40, and we'll continue with radial basis functions and coherent self-organizing map in the next session.
Yes, sir.
So over to you, Ganesh and Sharmila Kumari.
Yes, sir.
Any questions? It's my pleasure to answer.
Sir, we'll ask in the afternoon session, sir. We'll consolidate all the questions and ask in the afternoon.
Okay, fine. So we'll be getting back at 2 o'clock, right?
2 o'clock, sir. Yes, sir.
Yeah, sure.
Yeah. Dear participants, we shall now break for lunch. We will resume the afternoon session at sharp 2 o'clock. Thank you.
So thank you. I'll be back at 2.
Yes, sir. Yes, sir.
Thank you.
Thank you, sir.
ನಮಸ್ತೆ
ಸರ್.
ನಾನು ಮಧ್ಯಾಹ್ನ ಇರಲ್ಲ, ಸ್ವಲ್ಪ ಬೇರೆ ಏನೋ ಮೀಟಿಂಗ್ ಇದೆ ನಂಗೆ.
ಗುರು ಎಲ್ಲಿ ಹೊರಟ್ಬಿಡ್ತಾ ಇದ್ದೀರಾ?
ಮಧ್ಯಾಹ್ನ ಸ್ವಲ್ಪ ಬೇರೆ ಎಂಗೇಜ್ಮೆಂಟ್ ಇದೆ. ಆಮೇಲೆ ಆರಾಮ.
ಮತ್ತೆ ಗುರು ಹೇಳಿ.
ಇನ್ನು ಮಾಮೂಲಿ ಸರ್, ಹೇಳ್ಬೇಕು ನೀವೇ ಎಲ್ಲ.
ಏನಿಲ್ಲ ಇದೆ ಬೆಸ್ಟ್ ಕೆಲಸಗಳು, ಸುಮ್ಮನೆ ಆರಾಮಾಗಿರೋದು.
ಬಟ್ ಆನ್ಲೈನ್ ಒಂಥರ ರಿಸ್ಟ್ರಿಕ್ಟೆಡ್, ಕುತ್ಕೊಂಡ್ ಮಾತಾಡೋದಿದೆಯಲ್ಲ.
ಹೌದು.
ಅದಕ್ಕೆ ನೀವು ಆನ್ಲೈನ್ ಅಲ್ಲಿ ಹೇಳಿದ್ರೆ ಅವ್ರು ಏನ್ ಹೇಳ್ತಾರೆ ಅಂತ ಹೇಗೆ ಹೇಳಲಿಕ್ಕಾಗುತ್ತೆ
ಅಲ್ವಾ? ಹಿಂಸೆ ಸ್ವಲ್ಪ ಏನು ಮಾಡಕ್ಕಾಗಲ್ಲ. ಬಟ್ ದಿಸ್ ದ ಓನ್ಲಿ ವೇ ಕರೆಂಟ್ ಟೈಮ್ ಬೀಯಿಂಗ್.
ಅಲ್ಲ, ಇದು ಆಕ್ಚುಲಿ ಫಿಸಿಕಲ್ ಆಗಿದ್ರೆ ನಾವು ಬರಿಬಹುದು, ಅದನ್ನ ಬೋರ್ಡ್ ಅಲ್ಲಿ ಬರೆದು. ನನ್ಗೆ ಐ ಲೈಕ್ ಆಕ್ಚುಲಿ ರೈಟಿಂಗ್.
ಹೌದು, ನಿಮ್ ಸ್ಲೈಡ್ ನೋಡೋದಲ್ಲ ಗೊತ್ತಾಗತ್ತೆ ಆ ಪಾರ್ಟಿಸಿಪೆಂಟ್ಸ್ ಗೆ ಈ ಎಂಜಾಯ್ ರೈಟಿಂಗ್ ಅಂತ.
ಬರಿಬೇಕು, ಬರ್ದ್ರೆ ನಮ್ಗಿರೋದನ್ನ ತಲೆಗೆ ಕಲ್ಸ್ಬೋದು ಅವ್ರಿಗೆ. ಅದು
ಮ್ಯಾಥಮೆಟಿಕ್ಸ್ ಬರ್ದಾಗ್ಲೇ ಸರ್ ಅದು ಹೋಗೋದು ಒಳಗೆ.
ಅದು ಬರೀದೆ, ಅದು ಫ್ಲೇವರ್ ಸುಮ್ಮನೆ ಹೇಳ್ಬಿಟ್ರೆ ಬರೋದಿಲ್ಲ ಗುರು. ಪಿಪಿಟಿ ನನ್ಗೆ ಟೈಮ್ ಸೇವ್ ಆಗುತ್ತೆ ಅನ್ನೋದೊಂದು ಬಿಟ್ರೆ, ನಿಜವಾದ ಮೇಸ್ಟ್ರು ಬರ್ದ್ ತೋರ್ಸ್ಬೇಕು ಯಾವಾಗ್ಲೂ ಮ್ಯಾಥಮೆಟಿಕ್ಸ್ ಅನ್ನ. ಸೊ ಹಿಂಗೆ ನಡ್ಕೊಂಡು ಹೋಗುತ್ತೆ.
ಊಟ ಮನೆಗೆ ಹೋಗ್ತೀರಾ ಅಥವಾ ಕಾಲೇಜ್ ತಂದಿದ್ದೀರಾ?
ಎಲ್ಲಿ ಗುರು?
ಊಟಕ್ಕೆ ಮನೆ?
ಮನೇಲೆ ಇದ್ದೀನಿ ನಾನು, ಈಗ ರಜಾ ಕೊಟ್ಟಿದ್ದೀನಿ ಈಗ ನಾನು.
ಹೌದಾ?
ನಾನ್ 4 ವರ್ಷದಿಂದ ರಜೆ ತಗೊಂಡಿಲ್ಲ.
ನಾ ಆಫೀಸ್ ಇದೀರಿ ಅನ್ಕೊಂಡಿದ್ದೆ.
ಇಲ್ಲ, ಮನೆನೇ ಆಫೀಸ್, ಹೋಮ್ ಆಫೀಸ್ ಇದು.
ಫೈನ್, ಫ್ಯಾಂಟಾಸ್ಟಿಕ್ ಮಾಡಿ ಹಾಗಾದ್ರೆ.
ಮನೇಲೆ ಈಗ ಸ್ವಲ್ಪ ಕೆಲಸದ ವಾರ ಎಲ್ಲವೇ, ಮಂಡೆಯಿಂದ ಹೋಗ್ತೀನಿ ನಾನು.
ಸರಿ ಸರ್. ಹಾಗಾದ್ರೆ ಮಕ್ಕಳು ಇಲ್ಲೇ ಬಂದಿದಾರ, ಮನೇಲೆ ಇದಾರೆ ಮಕ್ಕಳು?
ಚಿಕ್ಕವಳು ಇಲ್ಲೇ ಇದ್ದಾಳೆ, ದೊಡ್ಡವಳು ಅಲ್ಲೇ US ನಲ್ಲೇ.
ಅಲ್ಲೇ ಅವಳು ಹೆಂಗಿದಾಳೆ ಅಲ್ಲಿ US ಅಲ್ಲಿ?
US ಚೆನ್ನಾಗಿದ್ದಾಳೆ ಅವಳು. ಅವಳದು ಶಿ ಇಸ್ ಡೂಯಿಂಗ್ ವೆಲ್.
ಕೋವಿಡ್ ಪ್ರಾಬ್ಲಮ್ ಇಲ್ಲ ತಾನೆ
ಅಲ್ಲಿ? ಕೋವಿಡ್ ಇದೆ, ಬಟ್ ಏನಂತಾರೆ ಅವ್ರು ಯಾರು ಕೇರ್ ಮಾಡಲ್ಲ ಅಂತಪ್ಪ. ಎಲ್ಲ ಆರಾಮ ನಡೀತದೆ ಅಂತ ಅವಳೇನೆ. ಯಾರು ಜಾಸ್ತಿ ತಲೆ ಕೆಡ್ಸ್ಕೊಳಕ್ ಹೋಗ್ತಿಲ್ಲ. ಇನಿಷಿಯಲ್ ಇದ್ದು ಪ್ರಾಬ್ಲಮ್ಗಳು ಇವಾಗಿಲ್ಲ ಗುರು.
ನಮ್ಮಲ್ಲೂ ಆಯ್ತಲ್ಲ, ಪಿಕಪ್ ಆಗ್ತಾ ಇದೆ ನೋಡಿ, ಹೋರಾಟ ಮಾಡ್ತಿದ್ದಾರೆ.
ಬಟ್ ಏನ್ ಗೊತ್ತಾ, ಮೈಸೂರ್ಲಿ ಎಲ್ಲಕ್ಕೆ ದೇಶದಲ್ಲಿ ಕಡಿಮೆ ಇದ್ರೆ ಮೈಸೂರು ಜಾಸ್ತಿ ಆಗ್ತಾ ಇದೆಯಲ್ಲ.
ಯಾಕೆ ಅನ್ಫಾರ್ಚುನೇಟ್ ಗೊತ್ತಾಗ್ತಿಲ್ಲಪ್ಪ.
ಅಲ್ಲ, ಇದು ಸ್ಕೇರಿ ಪಿಕ್ಚರ್, ಚಿಕ್ಕ ಸಿಟಿ ನಮ್ದು. ಇದು ಏನಾಗುತ್ತೆ ಅನ್ನೋದೇ ಅರ್ಥ ಆಗ್ತಿಲ್ಲ ಇದ್ರಲ್ಲಿ ನಮ್ಗೆ ಇವಾಗ,
ಅಲ್ವಾ? ಎಷ್ಟು 1000 ಚಿಲ್ಡ್ರೆ ನೆನ್ನೆನೋ ಮೊನ್ನೆನೋ. ಸರಿ ಸರ್, ಹಾಗಾದ್ರೆ ವಿಲ್ ಕ್ಯಾಚ್ ಯು ಲೇಟರ್. ಹಲೋ ಸರ್, ನಿಮ್ ಮ್ಯೂಟ್ ಆಗೋಯ್ತು. ನಿಮ್ದು ಅನ್ಮ್ಯೂಟ್ ಮಾಡಿ. ಸ್ಟಾಪ್ ಶೇರಿಂಗ್ ಸ್ಕ್ರೀನ್.
ಸೊ ಇವಾಗ ಇದು ಕೂತ್ಕೊಂಡು ಒಂದಷ್ಟು ಕೆಲಸ ಮಾಡೋಣ ಗುರು. ಇವಾಗ ಫ್ರೀ ಕೂತ್ಕೊಂಡು ನಮ್ಮಲ್ಲಿ ಪರಮ್ ಇದೆ, ಒಂದಷ್ಟು ಕೂತ್ಕೊಂಡು ಕೆಲಸ ಮಾಡೋಣ.
ಲೆಟ್ಸ್ ಡೂ ಒನ್ ಥಿಂಗ್ ಸರ್. ಸಮ್ ಬೇಸಿಕ್ ಮ್ಯಾಥಮೆಟಿಕ್ಸ್ ರಿಕ್ವೈರ್ಡ್ ಫಾರ್ ಮಿಷಿನ್ ಲರ್ನಿಂಗ್ ಅಂತ ಒಂದು ಕೋರ್ಸ್ ಡಿಸೈನ್ ಮಾಡೋ.
ಒಂದು ಕೋರ್ಸ್ ಡಿಸೈನ್ ಮಾಡ್ಬಿಟ್ಟು
ಒಂದು 48 hours ಆಫ್ ಲೆಕ್ಚರ್ಸ್.
ಹೌದು, ಅದೇ ತರ ಮಾಡೋಣ ಅದನ್ನ ಕೂತ್ಕೊಂಡು,
ಅಲ್ವಾ?
ಇದು ಬೇಸಿಕ್ ಕ್ಯಾಲ್ಕುಲಸ್, ಡಿಫರೆನ್ಷಿಯಲ್ ಈಕ್ವೇಶನ್ಸ್ ಇಂದ ಹಿಡಿದು ಲೀನಿಯರ್ ಆಲ್ಜಿಬ್ರಾ ಇಂದ ಹಿಡಿದು ಕೊನೆಗೆ ನಿಮ್ಗೆ ಇದಲ್ಲೂ ಸ್ಯಾಂಪಲ್ಸ್ಗಳು, ಎಕ್ಸ್ಪೆಕ್ಟೇಷನ್ ಮಿನಿಮೈಸೇಷನ್ಸ್ಗಳು, ಪ್ರಾಬಬಿಲಿಟಿ ಇದನ್ನ ಎಲ್ಲಾನು ಸೇರ್ಕೊಂಡ್ ಮಾಡ್ಬೇಕು ಅದನ್ನೆಲ್ಲಾನು.
ಹೌದು, ಅದಕ್ಕೆ ನಾನು ಹೇಳೋದು ಒಂದು 48 hours ಆಗುವಂತ ಕೋರ್ಸ್ ಮೆಟೀರಿಯಲ್ ಲೆಕ್ಚರ್ ಸೀಕ್ವೆನ್ಸ್ ಮಾಡ್ಬಿಟ್ಟು.
ನಮ್ಗೆ ಏನಂತಂದ್ರೆ ನಾಟ್ ಮೆನಿ ಪೀಪಲ್ ಕ್ಯಾನ್ ಶೋ ಫಿಸಿಕ್ಸ್ ಇನ್ ಮ್ಯಾಥಮೆಟಿಕ್ಸ್.
ಹೌದೌದು,
ಇದು ತೋರಿಸ್ಬೇಕು, ಅದನ್ನ ಸಣ್ಣದ್ರಲ್ಲಿ ತೋರಿಸಿದ್ರೆ ಅಲ್ಲಿಂದ ಏನಾಗುತ್ತೆ, ಇವ್ರಿಗೆ ರಿಸರ್ಚ್ ಅಲ್ಲಿ ಥಿಂಕಿಂಗ್ ಚೇಂಜ್ ಆಗುತ್ತೆ. ಅದು ಇಲ್ಲಾಂದ್ರೆ ಬರೀ ಯೂರಿಸ್ಟಿಕ್ ಏನೋ ಒಂದು ಹಾಕ್ಬಿಡು ಮಾಡೋ ಥೀಸಿಸ್ ಕೊಡೋ ತರ
ಎಲ್ಲ ಈಗ ಎಲ್ಲ ಟೂಲ್ ಇದೆ ಅಲ್ಲ ಸರ್, ಎವ್ರಿಬಡಿ ಇಸ್ ಯೂಸಿಂಗ್ ಇಟ್ ಆಸ್ ಬ್ಲಾಕ್ ಬಾಕ್ಸ್ ಅಷ್ಟೇ. ಇದು ರಿಯಲ್ ಆಗಿ ಅರ್ಥ ಮಾಡ್ಕೊಂಡು ಅದನ್ನ ಹೇಳಷ್ಟು ಅಥೆಂಟಿಕ್ ಆಗಿ ಜನಗಳು. ಅನ್ಫಾರ್ಚುನೇಟ್ಲಿ ಏನ್ ಗೊತ್ತಾ, ಸ್ಯಾಂಪಲ್ ಕೊಡ್ತಾರೆ, ಬಂದ್ ರಿಸಲ್ಟ್ ಟೇಬಲ್ ಫಾರ್ಮಲ್ ಇಟ್ಬಿಟ್ಟು ರಿಸಲ್ಟ್ ಬಂತು ಸರ್ ಅಂತ.
ನಾನು ರಿಸಲ್ಟ್ ಬರುತ್ತಲ್ಲ, ರಿಸಲ್ಟ್ ಯಾಕೆ ಬಂತು ಅಂತ ಕೇಳಿದ್ರೆ ಯಾರು ಆನ್ಸರ್ ಮಾಡಿಲ್ಲ ಇದುವರೆಗೆ. ರಿಸಲ್ಟ್ ಬಂದ್ಬಿಟ್ಟಿದೆ, ಬಟ್ ಹೆಂಗ್ ಬಂತು, ಯಾಕೆ ಬಂತು ಅಂತ
ಗೊತ್ತಿಲ್ಲ. ರಿಸಲ್ಟ್ ಬಂದ್ರೆ ಒಂದು ಟೇಬಲ್ ಹಾಕರೆ
ಅಷ್ಟೇ.
ಬೆಟರ್ ದನ್ ಸಂಬಡಿ ಅನ್ನೋದು ಕೊನೆಗೆ.
ಅಷ್ಟೇ, ಬೆಟರ್ ದನ್ ಸಂಬಡಿ. ಈಗ ಆಗೋಯ್ತು. ಈಗ ನಾವು ಒಂದು ಕೋರ್ಸ್ ಮಾಡೋಣ ಕೂತ್ಕೊಂಡು ಏನಾರು
ಮಾಡೋ ಅಂತ. ಈಗ
ಇದರದೆಲ್ಲ ಯೋಚನೆ ಮಾಡ್ತೀನಿ. ಫ್ರೀ ಇರ್ತೀನಿ, ನಾನು ಲ್ಯಾಬಲ್ಲಿ ಕೂತಿರ್ತೀನಿ, ಎಲ್ಲೋ ಬೇರೆ ಏನು ಕೆಲಸ ಒಪ್ಕೊಳ್ಳಲ್ಲ.
ಕೋರ್ಸ್ ಡಿಸೈನ್ ಮಾಡಿ ಅದಕ್ಕೆ ಮೆಟೀರಿಯಲ್ ರೆಡಿ ಮಾಡ್ಸೋಣ. ಶೇಖರ್ ವಿಲ್ ಆಲ್ಸೋ ಜಾಯಿನ್.
ಶೇಖರ್, ಎಲ್ಲರೂ ಒಂದು ಟೀಮ್ ಮಾಡ್ಕೊಂಡ್ಬಿಡೋಣ, ಎಲ್ಲರೂ ಸೇರ್ಕೊಂಡು
ಒಂದ್ 6 ಜನ ಟೀಮ್ ಮಾಡ್ಕೊಂಡು ಮ್ಯಾಥಮೆಟಿಕ್ಸ್ ಆಸಕ್ತಿ ಇರೋರನ್ನೇ ಸೇರಿಸ್ಕೊಂಡು ಒಂದ್ 6 ಜನನ 6 ಯೂನಿಟ್ ಮಾಡೋದು.
ಹೌದು,
ಈಚ್ ಯೂನಿಟ್ ವಿಲ್ ಬಿ ಕವರ್ಡ್ ಬೈ ಒನ್ ಇಂಡಿವಿಜುವಲ್.
ಒಬ್ಬೊಬ್ರು ಒಂದೊಂದು ಇಂಡಿವಿಜುವಲ್ ಅಲ್ಲಿ ಇಷ್ಟಿಷ್ಟು ಅವರ್ಸ್ ಅಂತ ಮಾಡ್ಬಿಟ್ರೆ
ದಟ್ ಕುಡ್ ಬಿ ಬೆಸ್ಟ್ ಸರ್ವಿಸ್ ಟು ದ ರಿಸರ್ಚ್ ಕಮ್ಯುನಿಟಿ.
ಹೌದು, ಬಟ್ ಇಷ್ಟು ಕಾಂಪ್ಯಾಕ್ಟ್ ಆಗಿ ಮ್ಯಾಥಮೆಟಿಕಲ್ ಇನ್ಸೈಟ್ ಕೊಡೋರು ನನಗೆ ಗೊತ್ತಿರಂಗೆ ಯಾರು ಮಾಡಿಲ್ಲ ಇಂಡಿಯಾದಲ್ಲಿ. ಸೊ ಇದನ್ನ ಮಾಡೋಣ ಗುರು. ನೆಕ್ಸ್ಟ್ ಮಂತ್ ಇಂದ ಕೂರ್ತೀನಿ, ಕೂತ್ಕೊಂಡು ಮಾತಾಡೋಣ.
ನೀವು ಫ್ರೀ ಆಗಿ ಸಿಗ್ತೀರಿ ಅಂದ್ರೆ ಐ ಆಮ್ ವೆರಿ ಹ್ಯಾಪಿ.
ನಾನು ಎಲ್ಲ ಏನೇನೋ ಕೊಡ್ತೀನಿ ಅಂತಂದ್ರು ನಾನು ಯಾವ್ದು ಬೇಡ ಅಂತ ಅಂದ್ಬಿಟ್ಟಿದ್ದೀನಿ. ನಾನು ಐ ವಾಂಟ್ ಟು ಬಿ ಓನ್ಲಿ ಪ್ರೊಫೆಸರ್ ಅಂತ. ಅಲ್ಲಿ
ಅಲ್ಟಿಮೇಟ್ ಈಗ ಯಾವ ಸೀನ್ ಎವ್ರಿಥಿಂಗ್
ಬೇಡ ಸಾಕು, ಬೇಡ. ನೀವು ಅದ್ ಹೇಳಿದ್ರಲ್ಲ, ಅದು ಎಕ್ಸಿಕ್ಯೂಟಿವ್ ಡೈರೆಕ್ಟರ್ದು ಮಾಡ್ಕೊಂಡ್ಬಿಟ್ಟಿದಾರೆ ಒಳಗಡೆನೆ. ಅದು
ಆಯ್ತು, ಅದು
ಅವ್ರಿಗೆ ಮನೋಹರ್ ಜೋಶಿ ರಿಲೇಟಿವ್ ಗೋಪಾಲ್ ಕೃಷ್ಣ ಜೋಶಿ ಅಂದ್ಬಿಟ್ಟು ಹುಬ್ಳಿ.
ಗೊತ್ತಾಯ್ತು ಬಂತು ಮೆಸೇಜ್.
ಅವೆಲ್ಲ ಕೊಟ್ಟಿದ್ದು ಅದನ್ನೆಲ್ಲಾನು ಕಷ್ಟ ಗುರು. ಅವೆಲ್ಲ ಎಲ್ಲ ಓಡಾಡಕ್ ಆಗಲ್ಲ ಅವೆಲ್ಲಾನು. ಬೇಡಪ್ಪ, ಏಮಂತ್ ನೋಡಿ ನಾವು ಸುಸ್ತಾಗ್ಬಿಟ್ಟಿವಿ, ಬೇಡ ಇದು. ಸಿಗೋಣ ಆಗಿದ್ಮೇಲೆ ಮಾಡಿ ಊಟ ಮಾಡಿ.
ಥ್ಯಾಂಕ್ ಯು ಸರ್.
ಓಕೆ, ಬೈ.